We stand on a world where two suns cross the sky, and right now, at this particular moment, the first of those suns touches the horizon far to the west. The landscape around us stretches in gentle hills and frozen plains, a world of ice and methane clouds, cold and distant, yet illuminated by the warm glow of a setting star. Above, the sky holds color unlike anything Earth produces, a blend of orange and amber light filtering through the thick atmosphere. While higher still, a second sun continues to shine, smaller and redder, waiting its turn to set. This place is real, orbiting two stars 1,000 light-years from Earth, and we have come here in mind to watch what happens when sunset arrives on a world with twin suns. The first sun, the larger of the two, appears as an orange disk, perhaps 2/3 the size of our sun, as seen from Earth, its surface showing the characteristic color of a K-type dwarf star. Cooler than our sun, but still bright enough to warm this distant world across millions of miles of empty space. The color it casts across the landscape creates warm tones on the ice below, orange light reflecting from frozen methane and water ice that covers the surface of this gas giant's upper cloud layers. The sun moves slowly toward the horizon, dropping by its own diameter every few minutes, the motion perceptible if we watch patiently, the ancient rhythm of rotation carrying this world through its day. The shadows it creates stretch long across the cloudscape, marking every rise and depression in the frozen methane haze, with lines of darkness that extend eastward, away from the setting sun. You are listening to the Drowsy Astronaut, where we explore the cosmos slowly and thoroughly, taking time to experience places that exist beyond our reach, but within our understanding. Tonight we visit worlds where multiple suns illuminate the sky, creating sunsets that happen more than once each day. And we will move gently through these alien landscapes without hurry or urgency. If you are settling in from wherever in the world you happen to be listening, perhaps leave a comment about your location and what draws you to these cosmic journeys at the end of your day. The like button and subscribe option are there if this kind of slow cosmic exploration brings you some quiet fascination. But we are not alone in creating shadows, and this is where the strangeness of this world becomes clear. The second sun, hanging perhaps 40 degrees above the eastern horizon, casts its own set of shadows from every feature in the landscape, creating a double pattern of light and dark that marks this world as fundamentally different from home. The second sun appears smaller, perhaps half the diameter of the first, glowing with the deep orange-red color of an M-type dwarf, a red dwarf star much cooler and dimmer than its companion. Its light adds to the illumination even as the first sun sets, maintaining brightness across the frozen landscape, ensuring that sunset here does not mean the immediate arrival of darkness. The two sets of shadows, one long and diffuse from the setting sun, one shorter and sharper from the elevated companion, cross and overlap in complex patterns that shift slowly as both stars move through their paths across the sky. The first sun continues its descent, now half hidden behind the distant horizon, the curve of this world blocking more of the orange disk with each passing moment. The light it provides begins to dim, not suddenly, but gradually, the landscape responding to the loss of this primary source by shifting in tone and character. Colors warm further toward red as the orange sun disappears and the red dwarf's contribution becomes more dominant, the world transforming subtly before our eyes, through nothing more than the changing balance of stellar illumination. The quality of light changes too, becoming softer as the harsher orange sunlight fades and the gentler red dwarf light remains, creating an atmosphere more like deep earth twilight, though the sky remains bright overhead. And then the first sun is gone, slipped completely below the horizon, the last curve of orange light vanishing and leaving only the red dwarf to illuminate this frozen world. The transformation feels significant despite the remaining brightness, as if something essential has departed, even though daylight persists. The shadows simplify, now cast only by the single remaining sun, the double shadow complexity resolving into a more familiar pattern, though the color remains alien. The landscape appears different now. Not darker necessarily, but changed in character, the orange tones replaced by deeper reds and browns. The ice taking on hues that Earth's ice never shows under our single yellow sun. The sky shifts too, the orange amber fading toward rust and crimson, the color of a sky illuminated by a red dwarf star, shining alone. Time passes, perhaps an hour by Earth's measure, though time feels different here in the slow rhythm of this world's rotation. And during this interval, the second sun continues its own journey toward the western horizon. The light it provides, while sufficient to see clearly and navigate easily, carries less intensity than the first sun offered, creating a dimmer day, a twilight period that stretches between the two sunsets. The temperature, already cold on this distant world, changes little, if at all, during this transition, as the thick atmosphere and the distant orbit from both stars maintain conditions far below anything comfortable by human standards. We watch the landscape under this single red sun, seeing how the light catches ice crystals in the upper atmosphere, creating subtle halos and refractions that add beauty to the alien sky. The red dwarf sun, smaller in appearance but moving along a similar path to its companion, begins to approach the horizon, following the first sun westward toward the same setting point. The motion continues steadily, unhurried, the rotation of this world carrying us around toward the night side at a pace determined by physics and angular momentum, rather than any consideration for observers. The shadows lengthen further as the sun drops lower, extending across greater and greater distances as the angle becomes more acute, until the landscape appears as a study in red light and black shadow. The contrast sharpening as the sun approaches the horizon line. The sky near the horizon brightens in deep crimson and orange red. The same sunset colors Earth shows, but shifted spectrally toward longer wavelengths, toward the red end of the spectrum that dominates when red dwarf stars provide the illumination. The second sunset proceeds with the same gradual certainty as the first, the red dwarf touching the horizon and beginning to sink, the disk of the star showing clearly against the darker sky, its surface perhaps showing dark spots and bright regions, though at this distance and through this atmosphere, such details blur into a uniform glowing circle. Half the sun disappears, then more, the light dimming now in a way it did not during the first sunset, because no other sun remains to maintain illumination. The landscape darkens perceptibly, the red light fading toward deep twilight, the shadows losing their sharpness as the light source weakens and diffuses. The sky begins to reveal stars, points of light becoming visible in the deepening darkness, the cosmic background emerging as the local stellar illumination fades. And then the second sun sets completely. The last arc of red light slipping below the horizon, and true night arrives on this world for the first time since we arrived. The darkness does not fall suddenly, but settles gradually, the way twilight fades on Earth, but extended in time, the thick atmosphere scattering the last light long after the sun itself has vanished. The stars grow brighter and more numerous as our eyes adjust, constellations unfamiliar because we observe from a different location in the galaxy, the patterns of stars rearranged by our 1,000 light-year displacement from Earth. The landscape fades into darkness, the frozen hills and methane ice plains becoming invisible except where starlight catches the brightest surfaces, creating a subtle glow that marks the terrain without revealing details. We have watched 2 sunsets, 2 separate farewells to daylight, each one distinct in character and timing, separated by an hour of red twilight between them. This experience, impossible on Earth, happens here every day, every rotation of this world, bringing the same sequence of events, the orange sun setting first, the red dwarf following an hour later, the darkness arriving only after both stars have departed below the horizon. The pattern repeats with the reliability of orbital mechanics, day after day, year after year, for as long as this world has existed, and for as long as it will continue to orbit its twin stars. The beauty of the double sunset, the shifting colors and changing shadows, the gradual transition from bright day through dimmed day to twilight to night, creates a rhythm unlike anything Earth produces. A daily cycle shaped by the presence of 2 stars rather than 1. This world is Kepler-16b, the first planet ever confirmed to orbit 2 stars, discovered by NASA's Kepler Space Telescope in the year 2011. The discovery confirmed what science fiction had long imagined, that planets could exist in binary star systems, orbiting both stars together in stable long-term orbits. The planet itself is a gas giant, roughly the size of Saturn, with no solid surface to stand on, but we imagine floating at the cloud tops where the atmospheric pressure might support a platform or a balloon, allowing us to observe the sky and experience the double sunset that defines this world's character. The 2 stars it orbits circle each other every 41 days, locked in a gravitational dance, while the planet orbits both of them together every 229 days, completing its yearly journey around the binary pair in a period between Earth's year and Mars's year. The coldness here, despite the presence of 2 suns, results from the distance and from the dimness of the stars themselves. Both stars are smaller and cooler than our sun, producing less energy. And the planet orbits far enough from them that their combined heat cannot warm this world above about -100 degrees Fahrenheit. The frozen methane and water ice that form the clouds we float above remains solid at these temperatures, creating a landscape of ice and haze lit by twin suns that provide light but not warmth. The atmosphere, thick with hydrogen and helium like Saturn's, would crush any unprotected visitor. But the cloud tops where we imagine ourselves positioned offer stable conditions and clear views of the sky where the twin suns move. The experience of being here, of watching the light change as first one sun and then the other sets, creates understanding that mere description could not provide. The color shifts become real, the doubled shadows tangible, the hour of red twilight between sunsets, a felt duration rather than an abstract number. The landscape transforms through the changing illumination, appearing different under the orange sun than under the red dwarf, different again when both shine together than when either shines alone. The progression from bright day through the two sunsets to night tells a story about this world's relationship with its stars, about the orbital mechanics that bring this pattern every day, about the strange beauty that emerges when gravity binds two stars together and a planet orbits them both. And now, having experienced the sunset sequence, having watched both stars disappear and darkness settle, we understand what makes this world unique, what distinguishes it from the single-sun worlds like Earth, where sunset happens once and day gives way directly to night. The twin stars create complexity in something as simple as the end of day, adding layers to the experience, creating intermediate states between day and night, where one sun has set, but another remains. The double sunset becomes the defining characteristic of this world, the feature that would dominate the experience of any visitor, the rhythm that shapes time and marks the passage of each day. Understanding why these two sunsets happen, why the stars set at different times and from similar directions, requires stepping back from the surface experience and seeing the larger system, the gravitational architecture that makes Kepler 1.6b possible. The two stars we watched set are not simply two unrelated suns that happen to share the same sky, but are gravitationally bound companions, orbiting each other in a relationship as old as the stars themselves. They dance around a common point in space, neither star staying still while the other orbits, but both moving in response to their mutual gravitational pull, creating a binary system that functions as a single unit despite being composed of two distinct objects. The stars orbit what astronomers call the barycenter, the center of mass of the two-star system, the balance point where their gravitational influences equal out. For stars of equal mass, this point lies exactly halfway between them, but Kepler 1.6's stars differ significantly in mass, with the larger orange K-dwarf containing about 69% of our Sun's mass, and the smaller red M-dwarf containing only about 20% of our Sun's mass. The unequal masses mean the barycenter sits much closer to the larger star, creating orbits where the massive orange star traces a relatively small circle, while the lighter red dwarf swings in a much wider arc, both stars completing their orbits in the same 41-day period because they remain gravitationally locked to each other. The orbital period of 41 days means these stars circle their common center of mass quite rapidly by stellar standards, completing more than 8 orbits during one Earth year. The stellar separation changing rhythmically as they swing around their elliptical paths. At their closest approach, the stars come within about 12 million miles of each other, about 1/8 the distance from Earth to the Sun, close enough that from the surface of one star, the other would appear enormous in the sky, dominating the view. At their farthest separation, they drift to about 16 million miles apart, roughly 1/6 of an astronomical unit, still close by stellar standards, but far enough that the view from one star would show the companion as a very large but more manageable disk rather than an overwhelming presence. From the planet's perspective, orbiting far enough from both stars that their individual motions barely affect the overall view, the two stars appear to move together across the sky, rising together in the east and setting together in the west, with only slight separation between them. The planet orbits at a distance of about 65 million miles from the barycenter, similar to Venus's distance from our Sun. But because it orbits the center of mass of the binary system, rather than a single star, its relationship to each individual star varies continuously. Sometimes, during the planet's orbit, it passes closer to the orange star, seeing that star appear slightly larger and brighter, while the red dwarf appears farther and dimmer. And at other times, the geometry reverses, bringing the planet closer to the red dwarf, while the orange star appears more distant. The stability of this arrangement, with a planet orbiting two stars that themselves orbit each other, depends on the planet maintaining sufficient distance from the inner binary pair. Too close to the stars, and the planet's orbit would become chaotic, disrupted by the constantly changing gravitational field as the stars circle each other, the perturbations eventually throwing the planet into an unstable trajectory that might eject it from the system or send it crashing into one of the stars. But at sufficient distance, the planet experiences the combined gravity of both stars as if they were a single object located at the barycenter. The individual motions of the stars averaging out over time and creating a stable gravitational environment that allows circular or nearly circular orbits to persist for billions of years. The distance that provides this stability depends on the separation of the binary stars themselves, with closer binary pairs allowing planets to orbit at proportionally closer distances, while wider binaries require planets to orbit much farther out to maintain stability. For Kepler-1.6, with the stars orbiting each other at 12 to 16 million miles apart, the planet's orbit at 65 million miles provides comfortable margin, sitting well beyond the chaotic zone where gravitational perturbations would dominate. Computer simulations of such systems show that planets generally need to orbit at least 3 times the binary separation to remain stable over billions of years. And Kepler-1.6b orbits about 4 to 5 times the binary separation, placing it firmly in the stable zone. The appearance of the two stars in the planet's sky varies depending on where the planet is in its orbit and where the stars are in theirs, creating a dynamic view that changes throughout the planet's year. Sometimes the stars appear closest together in the sky, separated by perhaps the width of 2 full moons as seen from Earth. Both stars visible but distinct. The orange star clearly larger and brighter. The red dwarf smaller and dimmer, but still obviously a disk rather than a point. At other times in the orbital cycle, the stars separate to several degrees apart, perhaps 5 or 6 moon widths, still appearing to move together, but showing more obvious individual character. The changing separation creates variety in the sky, preventing the view from becoming monotonous, despite following predictable patterns. The orbital velocity of the planet around both stars reaches about 21 miles per second, slower than Earth's 30 kilometers per second around the Sun, because Kepler-1.6b orbits at a greater relative distance from its star's combined mass. This velocity carries the planet around its elliptical path once every 229 days, defining the length of the planet's year, the time required for the world to complete one full circuit around the binary pair and return to the same position relative to the stars. During this year, the planet experiences whatever seasonal variations its axial tilt might create, though for this particular world, the tilt remains unknown, leaving open the question of whether summers and winters mark the passage of time, or whether the planet rotates with minimal tilt and experiences little seasonal change. The rotation of the planet itself, the spin that creates day and night, remains unmeasured because the planet's thick atmosphere and lack of surface features prevent astronomers from tracking rotation directly. The rotation could be fast, perhaps 10 to 15 hours, like Saturn's rapid spin, or slower, perhaps Earth-like, or even tidally locked with one face always toward the stars, though for a gas giant at this distance, tidal locking seems unlikely. Whatever the rotation rate, it determines how long the double sunset sequence takes to complete. How many hours pass from the first sunset to the second, and how much time elapses between sunset and sunrise when the stars return to the eastern horizon. The two stars themselves differ not only in size and color, but in fundamental properties that make them distinct stellar objects. The larger orange star, designated Kepler-16a, belongs to the spectral class K, making it cooler and smaller than our Sun, but still capable of fusing hydrogen into helium in its core, generating energy through nuclear fusion and radiating that energy into space as light and heat. Its surface temperature measures around 4,000 degrees Kelvin, about 700 degrees cooler than the Sun's surface, giving it the characteristic orange color we observed during sunset. The star contains about 69% of the Sun's mass, packed into a sphere, about 69% of the Sun's diameter, making its density similar to our Sun's despite the smaller size. The smaller red star, Kepler-16b, belongs to spectral class M, placing it among the red dwarfs, the smallest and coolest stars capable of sustaining hydrogen fusion in their cores. Its surface temperature measures only about 3,000 degrees Kelvin, giving it the deep orange-red color that dominated the landscape during the second sunset. The star contains only about 20% of the Sun's mass, making it roughly twice the mass of the minimum required for hydrogen fusion, and measures perhaps 20% of the Sun's diameter, creating a star roughly twice the size of Jupiter, but with 100 times Jupiter's mass concentrated into that volume. The red dwarf generates far less energy than the orange star, producing only about 1/20th the light and heat, but its lower mass means it will continue fusing hydrogen for hundreds of billions of years, outliving both the orange companion and our own Sun many times over. Together, these two stars create a binary system with a combined mass of about 89% of the Sun's mass, and their combined energy output roughly equals 40 to 50% of the Sun's luminosity, making the binary pair significantly dimmer than our Sun, despite being composed of two stars. This reduced luminosity explains why the planet remains so cold, despite orbiting at a Venus-like distance, as the stars simply do not produce enough heat to warm the planet the way Venus is warmed by our Sun. The planet receives perhaps 1/4 to 1/3 the stellar energy that Earth receives, comparable to the sunlight intensity at Mars's distance from our Sun, insufficient to melt the methane ice and warm the world above freezing. The discovery of this system in 2011 came through careful analysis of light from the stars measured by the Kepler Space Telescope, which detected periodic dimming events as the planet passed in front of the stars and blocked a small fraction of their light. The dimming pattern showed complexity because the binary stars also eclipse each other every 41 days, creating a regular brightness variation. And the planet's transits added additional dimming events at different intervals, creating a light curve that required sophisticated analysis to interpret. The confirmation that the additional dimming came from a planet rather than from another star or some instrumental artifact required months of careful work. But eventually the evidence became conclusive, and scientists announced the discovery of the first confirmed circumbinary planet, the first real Tatooine. The name Tatooine comes from the fictional desert planet in Star Wars, the homeworld of Luke Skywalker, depicted as orbiting two stars and showing iconic double sunset scenes. The connection between Kepler-16b and Tatooine captured public imagination when the discovery was announced, as science fiction became science fact, confirming that planets really can orbit binary stars, just as the movies imagined. The actual Kepler-16b differs dramatically from fictional Tatooine, being a cold gas giant rather than a warm desert world. But the essential feature, the orbit around two stars and the resulting double sunsets, matches the science fiction vision, validating the possibility that inspired storytellers long before astronomers found proof. The system continues to orbit and evolve according to the laws of physics, the stars circling their barycenter in 41-day rhythm, the planet completing its larger orbit every 229 days. The whole configuration persisting stably because the orbital mechanics satisfy the requirements for long-term stability. The planet will continue orbiting these stars for billions of years, barring some catastrophic intervention, like a close encounter with a rogue star passing through the system. And the double sunsets will continue happening with clockwork regularity. The orange star setting first, the red dwarf following, the pattern repeating day after day without variation. Standing on this world or floating above its clouds, we would grow accustomed to the rhythm of twin suns, to the doubled shadows and the changing colors as different stars dominate the sky. The strangeness would fade into familiarity with time, the double sunset becoming normal, the single sunset of Earth seeming strange and incomplete by comparison. The two stars would mark directions and time, the orange star defining the primary light source, the red dwarf providing the secondary illumination, both together creating the environment that shapes this world's character and determines its climate and appearance. The passage of a full day on Kepler-16b, from sunrise through the hours of daylight to the double sunset we have already witnessed, and onward through night to the next sunrise, creates a rhythm that would define existence on this world. The fundamental cycle of light and dark that marks time and structures activity for any life that might hypothetically exist in the clouds. We begin this day at dawn, when the first light appears on the eastern horizon, signaling the approach of the twin suns that have spent the night below the curve of this frozen world. The sky begins to brighten gradually, the deep black of night giving way to dark blue, then lighter blue, then hints of orange and amber as the approaching star's light scatters through the upper atmosphere before the stars themselves rise above the horizon. The light comes from both stars simultaneously as they travel together across the sky from the planet's perspective, rising together in the east just as they set together in the west. The first star to appear is the brighter orange one, Kepler 16a, its upper edge cresting the horizon and sending brilliant orange light across the frozen clouds, illuminating the methane haze and water ice crystals that form the visible surface of this gas giant's atmosphere. Minutes later, the second star follows, the red dwarf Kepler 16b, emerging above the horizon a few degrees away from its companion, adding its own deep orange-red illumination to the growing daylight. The two stars rise at slightly different positions along the eastern horizon because of their orbital separation, the exact positions depending on where each star sits in its 41-day orbit around their common center of mass, creating small variations in the sunrise configuration from day to day. Some mornings, the stars might rise almost perfectly aligned, appearing one above the other or nearly touching, while other mornings, they separate by several degrees, climbing the sky along slightly different paths, but still clearly moving together as a pair. As both stars climb higher, the sky brightens fully into day, the orange and red light combining to create an amber-toned daylight, unlike the white or yellow light of Earth's daytime sky. The shadows cast by every feature in the cloudscape multiply, each object creating two distinct shadows, one from each star, the shadows lying at different angles, depending on the star's separation in the sky. The double shadow effect creates visual complexity, patterns of light and dark that shift constantly as the stars move and their relative positions change. The shadows, sometimes nearly overlapping, when the stars appear close together, other times diverging at wider angles when the stars separate farther. Morning progresses, with both stars climbing steadily higher, their motion driven by the planet's rotation, the surface and clouds turning beneath the fixed stars, carrying us around from night side to day side and eventually back toward night again. The rate of this rotation remains unknown for Kepler 16b, but we imagine it rotating perhaps once every 15 hours, slightly faster than Earth, but slower than Saturn, creating a day length that would feel somewhat familiar, though shorter than Earth's 24 hours. The stars climb toward their highest point in the sky, the moment of local noon when they cross the meridian and begin descending toward the western horizon. And during this climb, the light grows brighter and the illumination more intense as the atmospheric path length through which the light travels decreases with the star's increasing altitude. The colors of the landscape shift as morning advances, the low-angle orange and red light at sunrise, giving way to more neutral amber tones as the stars rise higher and the illumination becomes more even. The frozen methane clouds and water ice surfaces reflect this changing light, appearing warmer orange at sunrise and moving toward paler amber and cream colors near noon, when both stars shine from high in the sky. The atmospheric haze scatters blue light more efficiently than red, the same physics that makes Earth's sky blue. But here, the incoming starlight contains little blue to begin with, starting already shifted toward orange and red, so the scattering creates amber and rust tones rather than blue, painting the sky in warm colors throughout the day. Noon arrives when the stars reach their highest point, the moment when shadows become shortest and the light most intense. Though even at maximum intensity, the illumination here remains dimmer than Earth's noon sunlight, because the two small cool stars together produce less light than our single larger, hotter sun. The temperature controlled more by the planet's thick atmosphere and greenhouse effects than by instantaneous sunlight intensity, changes little throughout the day, remaining locked at about -100 degrees Fahrenheit through noon, as through morning and evening. The unchanging cold defines this world, regardless of where the suns sit in the sky. The result of insufficient stellar energy reaching this distant orbit, combined with the planet's inability to retain what little heat arrives. After noon, the stars begin their descent toward the western horizon, retracing in reverse the path they followed during the morning climb, sinking gradually lower as the planet's rotation carries us around toward evening and eventual sunset. The afternoon proceeds as the mirror image of the morning, the light dimming slowly, the shadows lengthening, the colors warming back toward orange and red, as the atmospheric path length increases again, with the stars decreasing altitude. The two stars, maintaining their rough companionship throughout the day, continue to move together, sometimes appearing slightly closer or farther apart than at sunrise, depending on the details of their orbital motion, but always clearly paired, clearly part of a single binary system, rather than independent objects. The character of the afternoon light differs subtly from morning light, despite the similar geometry, an effect familiar on Earth, where morning and afternoon light can carry different qualities, even at identical solar elevations. The differences might arise from changes in atmospheric conditions over the course of the day, from variations in cloud density or haze distribution, or might simply be psychological. The knowledge that morning leads toward brighter day, creating different perception than the knowledge that afternoon leads toward darkening evening. On Kepler 1.6b, these effects, if they exist, would blend with the unique qualities created by having two light sources moving together, creating an atmosphere possibly unknown on any single star world. As afternoon progresses toward evening, we approach the double sunset we experienced at the beginning of this journey. The sequence where the larger orange star sets first, followed an hour later by the smaller red dwarf, the light changing and dimming in two distinct stages, rather than the single continuous dimming that marks sunset on Earth. The hour between the two sunsets creates a period of red twilight, a time when the landscape glows under the illumination of a single red dwarf star, everything bathed in deep orange-red light that transforms colors and softens details. This between-sunset period might hold particular significance in any culture that might hypothetically evolve here, a liminal time between full day and approaching night. A transition period with its own character, distinct from either the bright day or the dark night that bookend it. The second sunset completes the transition to night, the red dwarf slipping below the western horizon and leaving the sky to darken under starlight, alone. The night proceeds in silence, the frozen clouds unchanging beneath the unchanging stars, the temperature holding steady at its customary -100 degrees, because the thin, distant starlight provides negligible heat, even compared to the weak stellar radiation that bathes the planet during the day. The stars visible from here differ from Earth's stars because we observe from a position 1,000 light-years away, seeing different foreground and background stars, familiar constellations stretched and distorted by the displacement, new patterns emerging from the changed perspective. During night, the two stars remain below the horizon. Somewhere on the far side of the world, illuminating the night side while we experience darkness on what has become the day side in the planet's rotation. The stars themselves never stop shining, never cease their orbital dance around their common center of mass, continuing their 41-day circuit, regardless of whether we can see them from this particular location at this particular moment. The planet's rotation simply carries us through the shadow zone, the region where the bulk of the planet blocks starlight, creating the night that gives way to day when rotation carries us back around to face the stars again. The length of night depends on the planet's rotation rate, with faster rotation creating shorter nights and slower rotation creating longer ones. The relationship determined by simple geometry and the requirement that one full rotation must include both the day period when stars are visible and the night period when they are not. For our imagined 15-hour rotation, night might last 7 hours, balancing against an 8-hour day when both stars are visible above the horizon. The asymmetry arising from the stars taking time to rise and set, rather than appearing and disappearing instantaneously. The exact numbers depend on latitude as well, with polar regions experiencing different day-night ratios than equatorial regions, the usual complications of planetary geometry applying here just as they do on Earth. As night progresses toward dawn, the eastern horizon begins to brighten again, signaling the approach of another sunrise, another day, another cycle through the same pattern of twin stars rising together, climbing together, setting in sequence, and leaving night to rule until the next sunrise. The repetition creates reliability, the predictable rhythm that allows timekeeping and planning, the cycle that structures days into weeks and months and years through its endless iteration. Each day nearly identical to the last in its basic pattern. Each sunrise bringing the same 2 stars in slightly different configurations. Each sunset following the same double sequence. The reliability of orbital mechanics creating dependable patterns from the chaos of gas and gravity that formed this system billions of years ago. Living on such a world, experiencing this rhythm day after day, would create a relationship with the sky and with time different from what we know on Earth. The 2 stars would become familiar companions, known by their colors and sizes, distinguished by which sets first and which follows, their motions tracked across the sky throughout each day. The shadows they cast would become tools for navigation and timekeeping. The doubled shadows indicating directions and the changing shadow patterns marking hours. The between-sunset twilight would become a recognized part of the day, not an aberration but a regular feature, as normal as noon or midnight, a time with its own name and associations. The day's journey from dawn through morning, noon, afternoon, double sunset, and night to the next dawn creates the fundamental experience of time on Kepler 16b, the cycle that repeats approximately 229 times during each orbit around the twin stars. The pattern that has repeated billions of times since this planet formed, and will repeat billions more before the stars themselves begin to die. The rhythm continues regardless of whether anyone observes it, the light and shadow playing across the frozen clouds, in patterns determined by geometry and physics, beautiful and complex, and utterly reliable in their repetition. The heartbeat of a world that circles 2 stars instead of 1. We leave Kepler 16b behind now, the cold gas giant with its double sunsets fading into the distance as we travel to another world, Another planet orbiting not one, but two stars bound together by gravity. This new world lies in a different direction across the galaxy, about 3,000 light-years from Earth, orbiting in a system that holds not just one circumbinary planet, but three, a family of worlds all sharing the same twin suns. The system carries the designation Kepler-47, named for the 47th planetary system discovered by the Kepler mission. And within this system, the outermost planet, Kepler-47c, offers something Kepler-16b could not: warmth, or at least temperatures, close enough to water's freezing point that the possibility of habitable conditions emerges. Standing on or near Kepler-47c, or more accurately, floating at the cloud tops of this mini Neptune world about 4.7 times Earth's diameter, we find ourselves significantly farther from the twin stars than Kepler-16b orbited its suns. The planet circles both stars at a distance of about 165 million miles, roughly the same as Earth's distance from the Sun, taking 303 Earth days to complete each orbit around the stellar pair. The greater distance means the stars appear smaller in the sky than they did from Kepler-16b, no longer the prominent disks that dominated that closer world sky, but smaller, more modest circles of light that provide illumination without overwhelming the view. The two stars here differ from Kepler-16's stars in both size and character, with the primary being a Sun-like G-type star, though slightly smaller and cooler, measuring about 93% of our Sun's mass and radiating about 84% of its light. The companion star, like Kepler-16b, is a red dwarf M-type star, much smaller and dimmer than the primary, containing only about 1/3 of the Sun's mass and producing less than 1% of the Sun's light. The dramatic difference in brightness between the two stars creates an asymmetric pair where the Sun-like star dominates the illumination completely, providing nearly all the heat and light that reaches this planet, while the red dwarf contributes only a barely perceptible addition to the daylight. From our vantage point, floating above Kepler-47c's clouds, the Sun-like star appears as a disk about 70% the size of the Sun, as seen from Earth, bright and yellow-white, casting familiar-looking daylight across the atmospheric landscape. The red dwarf companion appears much smaller, perhaps 1/10 the primary star's diameter, glowing with deep red color, positioned in the sky several degrees away from the bright primary. The pairing creates a visual oddity. A normal-looking sun accompanied by a small red companion. The relationship clearly one of primary and secondary, rather than the more balanced partnership that Kepler-16b's orange and red stars displayed. The temperature here, warmed by the sun-like primary star, reaches levels much more hospitable than Kepler-16b's frozen environment, with estimates placing surface temperatures around 30 degrees Fahrenheit, just below the freezing point of water. This temperature puts the planet tantalizingly close to habitable conditions, cold by human standards, but not impossibly so. Well within the range where liquid water could exist with slight atmospheric pressure variations, or with the addition of antifreeze compounds like salts. The planet sits in what astronomers call the circumstellar habitable zone, the ring around the stars, where temperatures allow liquid water on a surface, though being a gas giant Kepler-47c itself has no surface for water to pool upon. But the possibility exists that this gas giant might host moons, and those moons if large enough to retain atmospheres, could potentially offer genuine habitable surfaces with liquid water oceans and temperate climates. The scenario parallels Jupiter's moon Europa or Saturn's moon Enceladus in our solar system, except that here the parent planet orbits within the habitable zone rather than far outside it, allowing any moon to receive enough starlight to warm its surface rather than relying solely on tidal heating from the parent planet. A large moon orbiting Kepler 47c would experience complex illumination from multiple sources, the two stars providing stellar light, the gas giant parent reflecting additional light when positioned appropriately, and tidal forces from the parent potentially generating internal heat. The view from such a hypothetical moon would surpass almost anything we have yet imagined, combining the double sun sky of a circumbinary world with the presence of a giant planet dominating half the sky, the moon being tidally locked to its parent, and therefore always showing one face toward the gas giant, while the stars circle overhead. From the hemisphere facing the planet, the gas giant would hang permanently in the sky, perhaps appearing 10 to 20 times larger than the moon appears from Earth, showing cloud bands and storms, and possibly rings if the planet developed them. The massive world rotating beneath unchanging patterns while the twin stars move across the background sky. The double sunset sequence would proceed with the giant planet as backdrop, the stars setting behind or beside the huge disk, creating spectacular visual combinations. The orbital period of 303 days creates a year nearly identical in length to Earth's, though the lack of axial tilt information prevents us from knowing whether Kepler 47c experiences seasons or maintains relatively constant conditions throughout its orbit. The planet's actual rotation rate remains unmeasured, as with Kepler 16b, leaving us to imagine days of any length, from rapid 10-hour spins to slower Earth-like 24-hour rotations, or even tidal locking, with one face always toward the stars. The rotation rate would determine the frequency of sunrises and sunsets, the length of day and night, and the overall rhythm of life on this world, or on any moons it might host. The system holds additional interest beyond Kepler 47c itself, as two other planets orbit closer to the stars, both discovered in the same analysis that revealed the outer planet's existence. Kepler 47b, the innermost planet, orbits very close to the binary pair, completing each orbit in only 49 days, likely scorched by the star's proximity, and far too hot for liquid water or comfortable conditions. Kepler 47d, the middle planet, orbits between the inner and outer worlds, taking 187 days to complete each orbit, sitting just inside the habitable zone where temperatures rise high enough to likely evaporate any surface water. The three planets create a system reminiscent of our solar system's inner planets, with small inner worlds and larger outer ones, though all three remain closer to their stars than Earth sits to the Sun, making the system compact compared to the vast spaces between our solar system's planets. From Kepler 47c, the inner planets would occasionally become visible as they transit across the stars, tiny dark circles crossing the stellar disks, creating mini eclipses where a planet temporarily blocks a small fraction of the starlight. These transits would be predictable, calculable events occurring at regular intervals determined by the orbital periods, offering opportunities for observation and scientific study, if any civilization developed the interest and technology to track them. The inner planet, Kepler-47b, would transit most frequently, crossing the stars every 49 days, while the middle planet, Kepler-47d, would transit every 187 days. The different periods creating complex patterns of when transits occur alone and when they might overlap with both planets visible simultaneously. The discovery of this three-planet circumbinary system in 2012, about a year after Kepler-16b's discovery, confirmed that circumbinary planets were not rare aberrations, but could occur in diverse configurations, including multi-planet systems where several worlds shared the same stellar pair. The findings suggested that planet formation around binary stars might follow similar processes to formation around single stars, with disks of gas and dust condensing into planets through gravitational collapse and accretion, the presence of two stars complicating but not preventing the formation of stable planetary systems. The discovery expanded the known inventory of circumbinary planets from 1 to 4 overnight. As Kepler-47's three planets joined Kepler-16b in the catalogue of confirmed worlds orbiting stellar pairs, standing on or near Kepler-47c and looking up at the twin stars, the experience differs noticeably from the view on Kepler-16b, despite both worlds orbiting binary pairs. Here the stars appear smaller due to greater distance, less dominating, more like normal suns that happen to come in pairs rather than overwhelming presences that define the entire sky. The dominant star looks and behaves much like the sun as seen from Earth, rising and setting in familiar fashion, casting familiar-looking light, creating daylight that would feel nearly normal to human eyes. The companion red dwarf adds a touch of novelty, a small red point accompanying the main sun, creating a second set of faint shadows, setting shortly after the primary in a double sunset sequence, less dramatic than Kepler-16b's, but still distinctive and beautiful in its own way. The warmer temperature makes this world feel more welcoming, despite the alien sky, the possibility of liquid water, and the position within the habitable zone, creating hope that either this world's moons or similar planets elsewhere might offer genuine habitats for life. The combination of twin suns and habitable conditions creates the closest real-world match yet found to the romanticized vision of Tatooine-style planets. Worlds where desert landscapes or ocean shores might bask under double sunlight, where life might evolve to track two suns across the sky, where civilizations might arise under skies fundamentally different from Earth's single-sun view. The discovery of Kepler-47c in the habitable zone confirmed that such worlds exist, making the science fiction dream a scientific possibility. The time spent on Kepler-47c allows us to appreciate variety among circumbinary worlds, to see that not all double-sun planets are frozen gas giants in frigid orbits, but that some achieve temperate conditions, that some orbit in multi-planet systems rather than alone, that each system develops its own character and configuration, despite sharing the common feature of twin suns. The universe produces diversity within every category, taking the basic theme of circumbinary planets and developing variations that span the range from hot to cold, from single planets to multiple planets, from red dwarf pairs to sun-like pairs, creating a zoo of worlds that all technically orbit binary stars but differ dramatically in their specific conditions and characteristics. And now, having experienced the frozen cold of Kepler-16b and the near-habitable warmth of Kepler-47c, we prepare to leave circumbinary orbits behind, temporarily, and visit a different configuration entirely, a world that orbits only one star of a binary pair, while a companion star shines from a distance, creating yet another variation on the theme of multiple suns in the sky. The configuration changes now, the orbital architecture shifting from planets that circle both stars together to planets that orbit just one star, while a second star orbits far away, providing light from a distance rather than sharing the center of the planet's gravitational allegiance. This arrangement, called an S-type orbit in the technical language of orbital mechanics, creates experiences different from the circumbinary worlds we have visited. As the planet maintains a normal relationship with one primary sun, while an exceptional relationship develops with a brilliant, distant companion. We travel now to the nearest star system to our Sun, the triple system of Alpha Centauri, located just 4.37 light-years from Earth, our immediate stellar neighborhood. The Alpha Centauri system contains 3 stars arranged in a hierarchical pattern, with 2 Sun-like stars designated Alpha Centauri A and Alpha Centauri B, orbiting each other in a relatively close binary pair, while a third star, Proxima Centauri, orbits the pair from a great distance of about 13,000 astronomical units, roughly 1/5 of a light-year away from its companions. The 2 inner stars, A and B, circle their common center of mass every 79.9 years, their separation varying from about 11 astronomical units at closest approach to about 36 astronomical units at their farthest separation, a distance range that spans from just beyond Saturn's orbit to beyond Neptune's orbit, if we imagine them in our solar system's scale. We focus now on a planet, real or imagined, orbiting Alpha Centauri B, the slightly smaller and cooler of the 2 Sun-like stars. Alpha Centauri B is an orange K-type star, containing about 90% of the Sun's mass and radiating about 50% of its light, making it dimmer and redder than our Sun, but still far larger and brighter than the red dwarf stars we encountered at Kepler-16b and Kepler-47. The planet we imagine orbiting it, whether the controversial Alpha Centauri BB claimed in 2012 and disputed later, or a different planet, yet undiscovered, circles at a distance, placing it in a potentially habitable zone, or at least close enough that the star appears as a proper sun in the sky, rather than a distant point of light. From the surface of this hypothetical world, or from a comfortable position floating above its clouds if it happens to be a gas giant, Alpha Centauri B dominates the sky as the primary sun. Appearing about 1.3 times larger than the Sun appears from Earth, due to the closer orbital distance required to receive comparable heat from the dimmer star. The star's orange color creates a slightly warmer toned daylight than Earth experiences, painting the landscape in hues shifted subtly toward amber and orange, though not so dramatically as Kepler-16b's deep orange light. The sunrise and sunset, when Alpha Centauri B rises and sets, proceed similarly to Earth's familiar patterns. A single sun emerging from the eastern horizon at dawn, climbing through the sky to noon, descending toward the western horizon, and setting to bring night. But the sky holds a second star, and this is where the experience diverges from Earth's and from any single star world we might imagine. Alpha Centauri A, the slightly larger and brighter companion, shines from somewhere in the sky, sometimes close to Alpha Centauri B, sometimes on the opposite side of the sky, its position and brightness varying throughout the 80-year orbital period as the two stars circle each other. At its brightest, when the binary orbit brings Alpha Centauri A closest to the planet and closest to alignment with Alpha Centauri B, the companion star outshines every object in Earth's sky, except the Sun and Moon, appearing perhaps 100 to 200 times brighter than Venus appears to us. Bright enough to cast noticeable shadows, bright enough to read by comfortably, bright enough to suppress most other stars in its vicinity. The shadows created by Alpha Centauri A, while much fainter than the shadows cast by the primary sun Alpha Centauri B, are nonetheless clearly visible, creating a second set of shadows from every object, doubling the shadow pattern in a way that recalls Kepler-16b's double shadows, but with much greater disparity in darkness. The primary sun casts deep, sharp shadows, the familiar kind that mark daytime on Earth, while the companion star casts much fainter secondary shadows, perhaps 20 to 50 times less dark than the primary shadows, visible but subtle. Noticeable primarily when the primary shadows are observed closely, and the second set becomes apparent alongside them. The double shadow effect becomes most obvious when both stars appear in the sky simultaneously, creating shadow pairs that spread from every rock, every tree, every structure, marking the presence of two light sources. The companion star's position in the sky changes throughout the planet's year, as the planet orbits Alpha Centauri B, and throughout the 80-year cycle as Alpha Centauri A orbits around the system's barycenter. Sometimes Alpha Centauri A appears in the sky at the same time as Alpha Centauri B, both stars visible simultaneously, the brilliant companion accompanying the primary sun across the daytime sky, adding its light to the day and preventing full darkness from ever falling. Other times, the orbital geometry places the stars on opposite sides of the planet, Alpha Centauri A rising as Alpha Centauri B sets, creating a situation where the primary sun sets in the west and darkness begins to fall. But before true night arrives, the companion star rises in the east, bringing enough light to maintain twilight conditions throughout the night, allowing navigation and observation without artificial light. The changing brightness and position of Alpha Centauri A creates seasonal variations, layered atop whatever axial tilt seasons the planet might experience. During years when the orbital geometry brings Alpha Centauri A closest to the planet, the companion contributes significantly to surface illumination and heating, possibly raising temperatures by several degrees and creating brighter nights when the companion appears opposite the primary sun. During years when Alpha Centauri A swings farthest from the planet, its contribution diminishes, still far brighter than any star or planet in Earth's sky, but reduced enough that temperatures might drop slightly, and nights might darken more completely when the companion's position allows true night to fall. The 80-year cycle creates long-term climate variations beyond anything Earth experiences, though the effect remains subtle compared to the dominant heating from the primary sun. The experience of day and night on this world creates rhythms unknown on Earth, where night falls reliably every day, and darkness blankets the land until sunrise. Here, night sometimes brings darkness and sometimes brings twilight, depending on where Alpha Centauri A sits in the sky, the variation creating unpredictability in nighttime conditions. Even though sunrise and sunset of the primary sun occur with perfect regularity. Some nights allow observation of stars and galaxies, the sky dark enough that the Milky Way becomes visible and constellations emerge clearly, while other nights, the companion star's brilliance washes out all but the brightest stars, creating a sky bright enough that only a few dozen of the very brightest stars shine through the glare. Timekeeping on such a world might develop different conventions than Earth's, perhaps recognizing multiple types of night. Dark night when both stars sit below the horizon, twilight night when the primary has set but the companion remains up, and perhaps no separate category needed for when both stars shine together during the day, as this simply counts as day regardless of whether one sun or two provide the illumination. The cultural and linguistic development might create specific words for these different conditions, recognizing distinctions that Earth-based languages never needed, because our single sun creates only one type of day and one type of night. The hypothetical civilization arising on such a world would develop astronomy and calendars tracking both the daily rising and setting of Alpha Centauri B and the long-term cycle of Alpha Centauri A's, changing position and brightness. The companion star would serve as a calendar marker, its position in the sky indicating the time of year, and its brightness indicating where in the 80-year cycle the system currently sits. Children would grow up watching Alpha Centauri A gradually shift position and brightness, seeing real-time evidence of orbital motion in a way Earth's sky never provides. As our nearest celestial objects beyond the Sun, the Moon and planets move too quickly or too slowly to create the same steady years-long progression that Alpha Centauri A would display. The view from this world, looking outward toward Earth, would show our Sun as a moderately bright star in the constellation we would not recognize. As the displacement of 4.37 light-years rearranges the familiar constellations significantly, stretching some and compressing others, creating new patterns that would require entirely new names and mythologies. Our sun would shine at magnitude 0.5, about as bright as the star Procyon appears from Earth, easily visible but not exceptionally bright, unmarked by any obvious feature that would distinguish it as special among the thousands of visible stars. Any civilization on an Alpha Centauri planet would need telescopes and careful observation to detect Earth as a tiny point of light near the unremarkable sun, and years of patient monitoring to measure Earth's orbital motion and confirm its planetary nature. The proximity of the Alpha Centauri system to Earth, a mere 4.37 light-years representing about 100,000 times the Earth-Sun distance, but only 4% of the distance to Kepler-16b, makes this system a prime target for future exploration, whether by robotic probes or by hypothetical future crewed missions. The Breakthrough Starshot initiative proposes sending tiny laser-driven spacecraft to Alpha Centauri at 20% of light speed, reaching the system in about 20 years after launch, potentially returning images and data about any planets orbiting these nearest stars. The discovery of such planets and the characterization of their conditions represents one of the most exciting possibilities in near-term astronomy, as confirming habitable worlds around our nearest stellar neighbors would transform the search for life from abstract speculation to immediate practical concern. Standing on this world, circling Alpha Centauri b, looking up at the orange primary sun and the brilliant distant companion, we experience a type of multi-star environment entirely different from the circumbinary worlds we visited earlier. Here, the primary sun dominates, providing nearly all the heat and most of the light, creating familiar patterns of day and night, sunrise and sunset, while the companion adds complexity and beauty without fundamentally changing the planet's relationship with its star. The S-type configuration creates a hybrid experience, mostly normal but with spectacular additions, a world where you grow accustomed to the primary sun until the moments when the companion blazes in the sky remind you that this system differs fundamentally from Earth's solitary sun arrangement. The time here feels less alien than time on Kepler 16b or Kepler 47c, despite those worlds' circumbinary orbits being more exotic in configuration. The familiarity of a single dominant sun, the normalcy of one sunrise and one sunset per day, the reliability of true night when both stars cooperate to sit below the horizon simultaneously, all create comfort and ease of adaptation that the circumbinary world's perpetual dual presence could not provide. Yet the companion star prevents complete familiarity, its brilliant light transforming some nights into twilight, its double shadows marking its presence during the day, its slow orbital dance creating long-term variations that remind us constantly that we stand under two suns, not one, regardless of how normal the primary sun appears. We leave the familiar orange warmth of Alpha Centauri b behind and travel to a world orbiting stars of dramatically different colors. A place where the quality of light transforms completely as different suns take turns dominating the sky. This world exists more in the realm of theoretical possibility than confirmed discovery, as astronomers have not yet found planets around the specific stellar pairing we imagine. But the configuration obeys physical law and represents a real possibility among the universe's planetary diversity. The planet orbits a hot blue-white A-type star, much larger and hotter than our Sun, while a red dwarf companion orbits at some distance, creating the maximum possible color contrast between primary and secondary stars. The blue-white primary star dominates with overwhelming brightness, pouring out perhaps 20 to 40 times the energy our Sun produces, its surface temperature reaching 8,000 to 10,000 degrees Kelvin compared to the Sun's 5,700 degrees. The star's heat pushes the habitable zone outward to distances comparable to Mars's orbit or beyond, requiring the planet to circle at perhaps 200 million miles to receive comfortable levels of warmth, rather than the 93 million miles that creates Earth's temperate climate. From this distance, the star appears slightly smaller than the Sun appears from Earth, but its brilliant blue-white color dominates the experience, creating a fundamentally different type of daylight than any world we have visited so far. Standing on this world's surface, whether rocky like Earth or floating at cloud level like the gas giants we have visited, the blue-white star overhead creates harsh, brilliant illumination, rich in ultraviolet and blue wavelengths, the kind of light that appears cold and sterile despite the actual warmth it provides. The landscape appears bathed in blue-white radiance. Colors shifted toward the cool end of the spectrum. Rocks appearing blue-gray, ice gleaming white-blue, any hypothetical vegetation likely taking on unusual colors as photosynthesis adapts to the blue-rich stellar spectrum. The shadows fall sharp and black, the high-contrast lighting creating dramatic definition between illuminated areas and shadow zones, the intensity of the light preventing the soft, gradual transitions that occur under dimmer, cooler stars. The sky itself appears different from Earth's familiar blue, as the atmospheric scattering that creates blue skies on Earth works with different input when the stellar spectrum peaks in blue and ultraviolet. The sky might appear very pale blue or even whitish blue, the scattering saturating the blue channels and washing out color, or might take on violet or purple tints if the atmosphere scatters shorter wavelengths efficiently, and the star produces enough ultraviolet to make those scattered wavelengths visible. The exact color depends on atmospheric composition and density, but regardless of specifics, the sky would appear strange to human eyes accustomed to Earth's deeper blue, created by our yellow sun's light scattering through nitrogen and oxygen. The red dwarf companion star, orbiting at a distance great enough to allow the planet's stable orbit around the primary, appears in this blue-white daytime sky as a small, deep, orange-red disk, far dimmer than the primary, but still clearly a star rather than a planet. Its color creating dramatic contrast against the blue-white illumination that floods the landscape. When both stars appear in the sky together, the color contrast becomes almost surreal. The blue, white, and red stars, separated by some distance, but both visible, both casting light. The landscape receiving illumination from opposite ends of the visible spectrum simultaneously. Objects would cast shadows from both stars, the primary creating the dominant sharp black shadows, while the red dwarf creates fainter, softer reddish shadows that only become visible in areas protected from the primary's overwhelming blue-white glare. The first sunset arrives when the blue-white primary star approaches the western horizon, its brilliant light dimming gradually as atmospheric path length increases and scattering removes some of the intensity. The sunset colors likely differ from Earth's familiar reds and oranges, as the blue-white star produces less red light to begin with, possibly creating blue and violet sunset hues, or perhaps pale orange if enough atmosphere scatters enough light to shift the spectrum. The disk sinks below the horizon, taking its harsh blue-white illumination with it, and the transformation begins. As the world shifts from blue-white daylight to red twilight, in a color change more dramatic than any we have yet experienced. With the primary star gone, the red dwarf becomes the sole illumination source, and its deep red light transforms the landscape completely, painting everything in warm crimson and rust tones, turning the blue-gray rocks to reddish-brown, making white ice appear pink or rose-colored, shifting vegetation from whatever colors it shows under blue-white light toward red or burgundy versions. The shadows, previously sharp and black, soften and become less defined, the red dwarf's dimmer light creating gentler illumination without the harsh contrast of the primary star. The sky darkens significantly, no longer the bright blue or white of daytime, but shifting toward deeper blue and purple transitioning to dark red near the horizon, where the red dwarf's light scatters most intensely. The psychological effect of this color transformation would be profound, as the world literally changes appearance when the primary star sets, becoming a different place under different illumination. Areas that appeared bright and exposed under blue-white light become shadowed and mysterious under red light, while areas that sat in deep shadow when the primary star shone might now receive illumination from the red dwarf approaching from a different angle. The temperature might drop somewhat as the primary's energy disappears and only the red dwarf's contribution remains, though the exact temperature change depends on atmospheric heat retention and the red dwarf's actual energy output, which, though small compared to the primary, might still contribute enough to prevent dramatic cooling. The time between the primary's sunset and the red dwarf's sunset creates a period of red twilight unlike anything Earth experiences, a prolonged transition where the world basks in single-color illumination. Everything rendered in the monochrome tones that photographers create artificially, but which here arise naturally from the stellar spectrum. The duration of this red twilight depends on the angular separation between the stars as seen from the planet, which varies throughout the planet's orbit and throughout the long orbital period of the stars around each other, creating seasonal variations in twilight length. Sometimes, the red dwarf might set minutes after the primary, creating a brief red twilight, while at other times, hours might pass between sunsets, creating extended periods of single-star illumination. The second sunset, when the red dwarf approaches and crosses the horizon, completes the transition to night, the red light fading gradually as the star sinks, the landscape darkening through deep red into blackness, the stars finally becoming visible as artificial or natural illumination, gives way to stellar background. The night sky, freed from both stars' glare, displays the cosmos in full glory, the Milky Way visible as a band of light, constellations appearing in unfamiliar configurations, but still beautiful and inspiring. The universe revealing itself as it does, from any world when local light sources dim and allow the distant light of other suns to appear. Sunrise reverses the sequence, with the red dwarf rising first, bringing red dawn that illuminates the eastern horizon and gradually spreads across the landscape, waking the world in crimson light before the primary star follows and transforms everything back to blue-white brilliance. The double sunrise, like the double sunset, creates transitions unknown on single-star worlds. Moments when the landscape holds one character, knowing it will soon transform to another. Anticipation built into the structure of each day through nothing more than orbital mechanics and stellar physics. Living on such a world would require adaptation to the dual-color regimes, with biology possibly developing different responses to blue, white, and red light. Plants perhaps conducting different types of photosynthesis under different stars. Animals perhaps showing different activity patterns in blue-white day versus red twilight. Vision would need to function across an enormous wavelength range, from the ultraviolet and blue of the primary star to the deep red of the dwarf, requiring either very versatile photoreceptors or multiple types of photoreceptors, each optimized for different spectral regions. The cultural development might create different associations for the two light types, perhaps considering blue-white day as work time and red twilight as rest time. Or, vice versa, the regular alternation creating natural divisions in daily activities. The artistic implications fascinate, as sculpture and architecture would appear completely different under the two light sources. Colors chosen for one illumination type, transforming under the other. Patterns and textures optimized for blue-white harshness, appearing muted under red softness, and vice versa. Painting and decoration would need to consider both lighting regimes, creating works that function under both, or deliberately choosing colors that transform dramatically as the light changes. Using the predictable color shift as an artistic element rather than fighting against it. The night sky viewed under red twilight would show different stars than the night sky viewed in full darkness, as the red dwarf's light would wash out fainter stars while allowing the brightest to shine through, creating a filtered version of the full stellar background. The experience of day on this blue and red world creates understanding of how profoundly stellar color affects the character and appearance of planets. How light frequency determines not just brightness, but the entire visual and atmospheric experience of a world. The contrast between blue-white and red illumination exceeds the contrast between Kepler-1.6b's orange and red suns, creating a transformation so complete that the same landscape becomes nearly unrecognizable as lighting shifts. The lesson carries forward. Worlds around different stars experience different realities, not just in temperature or habitability, but in the fundamental visual and sensory environment that shapes how those worlds appear, and how life, if it exists, must adapt to thrive. The complexity increases now as we travel to a world circling not 2 but 3 stars. A planet in a trinary system where the sky holds 3 suns of different colors and brightnesses, moving through intricate patterns determined by the gravitational relationships binding them together. Such systems exist throughout the galaxy, with roughly 10% of stars belonging to triple or higher order multiple systems, creating environments where the orbital mathematics becomes elaborate, and the sky displays stellar configurations that binary systems cannot produce. We imagine ourselves on a world where a close binary pair of yellow and orange stars acts as the primary suns, while a red dwarf third star orbits the pair from greater distance, creating a system that produces 3 separate sunrises and sunsets each day. The 2 primary stars, locked in tight orbit around each other, circle their common center of mass every 20 days, maintaining a separation of about 15 million miles. Close enough that from the planet's vantage point, they appear separated by perhaps 5 to 7 degrees, about 10 to 14 times the width of Earth's moon. The yellow star, a G-type like our sun but slightly smaller, provides most of the system's light and heat, while the orange K-dwarf companion contributes about 40% as much energy. The two together creating combined illumination about 1.4 times our sun's output. The planet orbits both stars together at a distance of about 100 million miles, taking roughly 250 days to complete each orbit, placing it comfortably in the habitable zone created by the binary pair's combined radiation. The third star, the red dwarf, orbiting the entire binary planet system from a distance of perhaps 200 astronomical units, comparable to the distance from our Sun to the outer edge of the Kuiper Belt, contributes very little energy to the planet, but adds visual and temporal complexity to the sky. From the planet's surface, this distant red dwarf appears small, roughly the size the Sun appears from Neptune, but much brighter than any planet in Earth's sky, bright enough to cast faint but measurable shadows, bright enough to suppress stars in its immediate vicinity, a presence impossible to ignore despite its distance. The red dwarf orbits the binary pair on a timescale of thousands of years, moving slowly enough that its position in the sky remains nearly constant from day to day, but shifts perceptibly over months and years, gradually working its way around the sky over centuries. Standing on this world's surface, perhaps on a rocky terrestrial planet or a large moon orbiting a gas giant, we watch the sky progress through a day, unlike anything encountered on binary worlds. The day begins with the first sunrise, the yellow G-type star emerging from the eastern horizon, its bright disk climbing into the sky and bringing familiar-looking yellow daylight to the landscape. Minutes or hours later, depending on the current phase of the binary orbit and the planet's rotation rate, the orange K-dwarf follows, rising from a position several degrees away from where the yellow star rose, adding its own orange-tinted light to the brightening day. The two stars climb together, but separately, maintaining their spacing as they cross the sky, their combined light creating illumination brighter than either star alone, but not dramatically different in color from what the yellow star provides, as its greater luminosity dominates the spectrum. Both primary stars cast shadows throughout the day, creating the doubled shadow pattern we have seen on other multi-star worlds. Though here, the shadows remain more nearly equal in darkness because the two stars' brightnesses differ by less than a factor of 3, rather than the factors of 10 or more that separated stars on some worlds we visited. The shadows cross at angles determined by the stars' separation in the sky, sometimes nearly parallel when the stars appear close together in their orbit, other times diverging at wider angles when their orbital motion separates them farther. The shadow patterns shift throughout the 20-day binary orbital period, creating variations that repeat regularly, allowing observers to track binary phase through shadow behavior without needing to measure stellar positions directly. The third star, the distant red dwarf, hangs somewhere in the sky throughout the day, its position depending on where it sits in its 1,000-year-plus orbit around the system. Sometimes it appears in the daytime sky, along with the two primary stars, adding a third set of faint shadows to the landscape, creating triple shadows from every object. 3 parallel or diverging lines of darkness, marking the influence of 3 separate light sources. Other times, the red dwarf's orbital position places it on the opposite side of the sky from the binary pair, rising when they set and setting when they rise, creating a situation where 3 separate sunset or sunrise events occur spread across many hours, as first one primary star sets, then the other, then much later, the red dwarf follows. The first sunset arrives when the yellow star approaches the western horizon, its path across the sky determined by the planet's rotation and modified slightly by the orbital motion of the binary pair. The star sinks below the horizon, taking its yellow light and its set of shadows with it, leaving the orange K-dwarf as the primary illumination source. The landscape shifts in color, warming toward orange as the remaining star's spectral signature becomes dominant, shadows consolidating from 2 sets to 1 as the yellow star's contribution disappears. The light dims somewhat, as the orange star alone provides less illumination than both together, but the day continues, maintained by the surviving primary star. Time passes, perhaps an hour or 2, depending on the details of the binary orbit and how the star's paths cross the sky. And the second sunset approaches as the orange star follows the yellow star toward the western horizon. This second primary star sunset transforms the world more dramatically, as the remaining light comes only from the distant red dwarf, assuming its orbital position places it above the horizon at this time. The landscape shifts from orange daylight to deep red twilight as the orange star disappears, colors transforming as we have seen before when red dwarf light dominates. Everything taking on crimson and rust hues, blue objects appearing nearly black, as the red-shifted spectrum contains little energy at short wavelengths. The interval between the second primary star sunset and the red dwarf sunset, if the geometry is aligned to create such a period, produces a unique form of twilight, dim and red, but sufficient to maintain visibility and basic navigation, the world holding in a suspended state between day and night. The duration of this red twilight varies enormously, depending on the red dwarf's current position in its orbit, sometimes lasting minutes when the red dwarf sits near the horizon, other times lasting all night when the red dwarf reaches a high point in the sky and remains visible throughout the period that rotation carries the primary stars below the horizon. During portions of the year when the red dwarf never sets, true night never arrives, the red dwarf maintaining continuous red twilight conditions throughout the entire rotation period, creating weeks or months when darkness never falls, despite the primary stars setting normally each day. The third and final sunset, when the red dwarf eventually approaches and crosses the horizon, brings true darkness to those portions of the year when the red dwarf's position allows it to set. The transition from red twilight to night completes the sequence of 3 sunsets. The landscape, dimming through stages from bright multi-star day, through orange single-star day, through red twilight to final darkness. The stars emerge, the familiar background of the galaxy becoming visible, constellations appearing in patterns unique to this location in space. The night proceeds in silence and stillness, the temperature dropping gradually if the atmosphere allows, the surface cooling as stellar input ceases and radiation to space continues unabated. Sunrise reverses the entire sequence, with the red dwarf rising first if its position requires it to set, bringing red dawn to the landscape, followed eventually by the orange K-dwarf, rising and transforming red to orange, followed finally by the yellow G-type star rising and bringing full daylight in familiar colors. The triple sunrise creates a prolonged dawn, the landscape brightening in stages, colors shifting through the spectrum, from red through orange to yellow-white, the shadows multiplying from 1 to 2 to 3 as each star adds its contribution. The full sequence of 3 sunrises and 3 sunsets creates a daily rhythm of remarkable complexity, with 6 distinct transition events occurring each rotation rather than the 2 transitions that mark Earth's simple sunrise and sunset. The timekeeping challenges on such a world would surpass those on binary worlds, as the question of when day begins and night ends becomes ambiguous when 3 separate celestial objects cross the horizon at different times. Cultural conventions might define day as beginning when the first primary star rises, treating the red dwarf as insufficient to constitute daylight, or might recognize 3 types of day: full day when both primaries and the red dwarf shine, partial day when only the primaries shine, and red day or red night when only the distant red dwarf provides light. The development of calendars and time systems would need to track multiple cycles: the planet's rotation, the 20-day binary orbital period, the 250-day planetary orbit, and the multi-thousand-year orbit of the red dwarf, creating layered timekeeping of extraordinary complexity. Navigation under such skies would offer both advantages and complications, as three separate celestial objects provide reference points that their complex relative motions create ambiguity. The primary binary pair would serve as the main directional indicator, rising in the east and setting in the west with predictable regularity, while the red dwarf's slow drift across the sky over years would make it useful for long-term tracking, but unreliable for immediate orientation. Mariners or travelers on such a world might develop elaborate navigation techniques, tracking all three stars and using their combined positions to determine location and direction, creating star charts far more complex than Earth's single-sun navigation requires. The beauty of such a sky would be undeniable. Three suns of different colors, hanging at different positions, their light combining and separating as they move, the shadows they cast creating intricate patterns, the transitions between different illumination states, providing variety that single-star and binary star skies cannot match. The visual richness would inspire art and mythology, with cultures likely developing elaborate stories about the three stars and their relationships, personifying them, perhaps as family members, or rivals, or companions, using their motions and configurations to mark seasons and events, and organize societal activities. The direct visibility of three-body dynamics in the sky would make such worlds natural laboratories for developing intuitive understanding of gravitational interactions, potentially accelerating scientific development as observable evidence of complex mechanics appears nightly overhead. Standing on this trinary world and watching the three suns move through their paths, we experience the maximum practical complexity that stable planetary systems can maintain, as systems with four or more stars rarely achieve the hierarchical arrangements necessary for stable planetary orbits. The three stars here represent perhaps the limit of what planets can orbit while maintaining long-term stability, creating environments that push the boundary of how complex multi-star sky patterns can become, while still allowing worlds to exist. The experience creates appreciation for the organizational principles that govern stellar systems, the hierarchies and separations that allow chaos to resolve into stable patterns, the ways that gravity creates order from the random distributions of mass in star-forming regions. We return now to familiar territory, to the star system closest to our Sun, and therefore the multi-star system nearest to Earth, a place we touched upon briefly, but deserve to explore more thoroughly. The Alpha Centauri system, sitting just 4.37 light-years from our solar system, represents our immediate stellar neighborhood, the first system any interstellar probe leaving our solar system would logically visit. The system consists of three stars, arranged in two levels. Alpha Centauri A and Alpha Centauri B form a relatively close binary pair, orbiting each other every 79.9 years, while Proxima Centauri, a red dwarf, orbits both from a distance so great that its membership in the system remained uncertain for decades, until proper motion studies confirmed the gravitational bond. Alpha Centauri A, the brightest star in the system and the fourth brightest star in Earth's night sky, exceeds our Sun slightly in both mass and luminosity, containing about 1.1 times the Sun's mass, and radiating about 1.5 times the Sun's light. The star's spectral type, G2V, matches our Sun's exactly, making Alpha Centauri A perhaps the most Sun-like star we know, a stellar twin differing only slightly in details. Alpha Centauri B, the second star of the binary pair, is smaller and cooler, a K1V orange dwarf, containing about 90% of the Sun's mass and producing about 50% of its light. Together, the two stars create a binary system brighter than our Sun alone, the combined light exceeding solar output by about 1.6 times when both stars contribute. The orbital characteristics of the binary pair create a dynamic relationship where the star's separation varies from 11 astronomical units at closest approach to 36 astronomical units at maximum separation, swinging through this range every 79.9 years in an elliptical orbit, with significant eccentricity. At closest approach, the stars come within about 1 billion miles of each other, roughly the distance from our Sun to Saturn, while at maximum separation, they drift to about 3.4 billion miles apart, roughly the distance from our Sun to Uranus. The varying separation means that from a planet orbiting one star, the companion would appear to change size and brightness dramatically over the 80-year cycle, sometimes appearing as a brilliant disk, rivaling the primary Sun in apparent size. Other times, shrinking to a smaller, but still exceptionally bright point. Proxima Centauri, the third member of the system, orbits the binary pair at an average distance of about 15,000 astronomical units, roughly 0.2 light-years or 12 trillion miles, far enough that light takes about 37 hours to travel from Proxima to the binary pair. This enormous separation places Proxima in a very wide orbit that takes perhaps 500,000 to several million years to complete. The uncertainty arising because we observe only a tiny fraction of one complete orbit and must extrapolate the full period from limited data. The star itself is a small red dwarf, spectral type M5.5V, containing only about 12% of the Sun's mass and producing only 0.17% of the Sun's light, making it far dimmer than either Alpha Centauri A or B, though still bright enough to illuminate any planets orbiting it. Proxima holds special significance because it hosts at least one confirmed planet, Proxima Centauri B, discovered in 2016 through radial velocity measurements showing the subtle wobble the planet's gravity creates in the star's motion. The planet orbits Proxima every 11.2 days at a distance of about 4.7 million miles, roughly 7 million kilometers, close enough that despite Proxima's dimness, the planet receives enough energy to potentially maintain liquid water on its surface, if atmospheric conditions allow. The planet's mass, estimated at 1.3 times Earth's mass, suggests a rocky composition similar to Earth's, raising the possibility that Proxima b might be a habitable terrestrial world, the closest potentially habitable planet to our solar system. Standing on Proxima b, we would see a sky fundamentally different from any we have visited so far, dominated not by the close red dwarf parent star, but by the extraordinary sight of the Alpha Centauri binary pair. The two stars would appear together as a brilliant double star, too close together to resolve as separate disks to the naked eye from Proxima b's great distance, but clearly showing two distinct points of light separated by a small angle. At the system's configuration, giving maximum angular separation, the two stars might separate by about 5 to 7 arcseconds, just beyond the resolution limit of human eyes, but easily split by even small optical aid into the yellow-white Alpha Centauri A and the orange Alpha Centauri B, both shining brilliantly enough to dominate the night sky completely. The combined brightness of the Alpha Centauri pair, as seen from Proxima b, would exceed the brightness of any object in Earth's night sky, except the Sun and Moon, appearing perhaps 300 to 400 times brighter than Venus appears to us, bright enough to cast noticeable shadows, bright enough to read by easily, bright enough to illuminate the landscape in perpetual twilight whenever the double star appears above the horizon. The color would blend yellow and orange, creating an amber or warm white appearance, the combined spectrum of the two stars mixing to produce illumination richer in longer wavelengths than our Sun alone, but still containing significant blue and green components from Alpha Centauri A's. Contribution. Proxima itself, the parent star, would dominate the sky in a different way, appearing about 3 times larger than the Sun appears from Earth due to the close orbital distance, its deep orange-red disk covering significant angular space and providing the heat and light that maintain any surface conditions on the planet. The star's color would paint the landscape in red and orange tones, creating a visual environment similar to the red dwarf worlds we have imagined, with Rayleigh scattering in any atmosphere likely producing pink or reddish skies rather than blue. The planet is likely tidally locked to Proxima due to the close orbit and the tidal forces involved, meaning one hemisphere would permanently face the star, while the other would experience eternal darkness broken only by the light of the Alpha Centauri pair, rising and setting as the planets tidally locked. Rotation carries different longitudes around the terminator. The view from the day side of a tidally locked Proxima b would show Proxima hanging permanently overhead or at a fixed position in the sky, depending on longitude, the star never rising or setting, maintaining constant illumination modulated only by any weather patterns or atmospheric variations. The Alpha Centauri binary would rise and set normally, circling through the sky every 11.2 days as the planet completes its orbit, the double star sometimes appearing in the sky, along with Proxima, sometimes opposite the parent star, and therefore rising when Proxima sets for observers on the terminator zone. The eternal day under Proxima's red light would receive occasional additional illumination from the Alpha Centauri pair, creating periods of brighter, warmer white light when the double star climbs high in the sky. The night side, permanently shadowed from Proxima's direct light, would experience perpetual darkness, broken only by the Alpha Centauri binary's light, when the double star appears above the horizon. The binary would rise and set on an 11-day cycle, spending roughly half that time visible and half below the horizon, creating alternating periods of illumination and complete darkness for the night side. During the times when Alpha Centauri shines, the night side would glow in amber twilight, bright enough to see clearly, warm enough perhaps to maintain some temperature above the deep cold that otherwise would dominate the permanently shadowed hemisphere. The twilight belt between eternal day and eternal night would experience the most variation, seeing Proxima permanently on the horizon, while the Alpha Centauri binary rises and sets, creating complex lighting that combines red dwarf horizon illumination with occasionally bright amber double star light. The potential habitability of Proxima b remains uncertain. As the close orbit exposes the planet to strong stellar winds and frequent flares from the active red dwarf, radiation that could strip atmospheres or harm surface life unless protective mechanisms exist. The tidal locking creates temperature extremes between day and night hemispheres, unless atmospheric circulation redistributes heat efficiently, potentially creating a frozen night side and a scorched day side, with only the twilight regions maintaining moderate temperatures. Despite these challenges, the planet's position in the habitable zone and its terrestrial mass make it one of the most interesting targets for characterization and eventual exploration, a potentially habitable world at our cosmic doorstep. From Earth, Alpha Centauri appears as a single bright star in the southern constellation Centaurus, the third brightest star in the night sky and the brightest star in the constellation, though it lies too far south for observation from much of the northern hemisphere. The two components, A and B, appear separated by enough distance that even small telescopes resolve them as distinct stars, creating one of the most beautiful double star systems in the sky. Proxima, far fainter and separated by 2 degrees from the binary pair, requires a telescope to see and appears as an unremarkable red dot without obvious connection to the brighter stars. Though careful measurement shows all 3 share the same proper motion through space, moving together and confirming their physical association. The proximity of Alpha Centauri makes it the primary target for proposed interstellar probe missions, with the Breakthrough Starshot initiative planning to send tiny laser-driven spacecraft to the system at 20% of light speed, reaching Alpha Centauri in about 20 to 25 years after launch. Such probes could photograph any planets orbiting the stars, measure their atmospheres and surface conditions, and transmit images and data back to Earth, the radio signals taking another 4.3 years to return, creating a roughly 30-year mission from launch to data receipt. The prospect of photographing planets around Alpha Centauri within our lifetimes transforms these stars from distant abstractions to places we might genuinely know, worlds we could see rather than merely infer. Standing on Proxima b and looking toward Earth, our Sun would appear as a moderately bright star, visible in the constellation Cassiopeia from the Alpha Centauri perspective. Bright enough to see easily, but not exceptionally brilliant, unremarkable among the thousands of visible stars. Any civilization on Proxima b observing the sky would need patience and precision to detect Earth as a faint point near that unremarkable star, requiring careful measurement over years to confirm Earth's orbital motion and characterize its properties. The communication time lag, 4.3 years each way, would make conversation impossible, but would allow one-way transmission of information, messages, or cultural exchanges, assuming both civilizations developed the interest and technology for such contact. The Alpha Centauri system, familiar to us as our nearest stellar neighbors, yet still profoundly distant at 4.37 light-years, represents both the accessibility and the challenge of interstellar exploration. Close enough that we can imagine visiting within conceivable timeframes. Distant enough that the journey would still require technologies we have not yet developed, and commitments spanning generations. The three stars continue their ancient orbital dances, Alpha Centauri A and B circling each other every 80 years, Proxima drifting in its vast orbit around them, planets perhaps orbiting each star, waiting to be discovered and characterized, and someday perhaps to receive visitors from the solar system that lies 4 light-years away. The story of how we discovered planets orbiting binary stars, how we confirmed that worlds like Kepler 16b and the others we have visited actually exist, rather than remaining theoretical possibilities, unfolds across years of patient observation, technological development, and careful analysis that gradually transforms speculation into verified fact. The journey begins with theory, with scientists in the 1990s asking whether planets could form in binary star systems, given the complex gravitational environment that 2 orbiting stars create, and whether any planets that did form could maintain stable orbits over billions of years without being ejected or destroyed by the competing gravitational pulls. The theoretical work showed that planets could indeed orbit binary stars stably, if they satisfied certain conditions, with the primary requirement being that the planet orbit either very close to one star, well within the binary separation, so that the second star's influence remained a distant perturbation, or much farther out, orbiting both stars together at a distance that made the binary pair effectively behave as a single gravitational source. The intermediate region between these zones, where neither configuration offered stability, became known as the chaotic zone, a region where perturbations from the 2 stars would create such complex dynamics that planetary orbits would destabilize over relatively short astronomical timescales, either ejecting the planet from the system or sending it crashing into one of the stars. Armed with theoretical predictions that stable orbits existed, astronomers began searching for actual planets. Though the technology for detecting planets around other stars remained primitive in the 1990s, with only a handful of exoplanets known at all. The breakthrough came with NASA's Kepler mission, a space telescope launched in March 2009, with one specific purpose: to find Earth-sized planets in the habitable zones of other stars by detecting the tiny dips in starlight that occur when a planet passes in front of its star from our point of view. This transit method had already proven successful for finding planets around single stars, and the Kepler team recognized that the same approach might work for binary stars, despite the added complexity. The challenge lay in distinguishing planet transits from the eclipses that binary stars create naturally as they orbit each other. When one star passes in front of the other, from our viewpoint, the combined light from the system dims significantly, creating a dip in the light curve that the binary eclipse produces every orbital period. Planet transits create much smaller dips, reducing the light by perhaps 1% or less, depending on the planet's size relative to the stars. And these tiny signals must be separated from the much larger binary eclipse signals and from countless other sources of brightness variation, including star spots, instrumental noise, and cosmic ray hits on the detector. The computer algorithms required to analyze binary star systems evolved to handle this complexity, searching for patterns that repeated, with periods different from the binary orbital period, looking for the telltale signature of a third body orbiting the system. The analysis required modeling the binary system precisely, calculating exactly how much light each star contributes, how the eclipses affect the total brightness, and then searching the residual data after removing the binary signal for evidence of additional periodic dimming. The computational challenge meant that binary systems received lower priority initially as Kepler focused on the simpler task of finding planets around single stars. But a dedicated team of scientists continued working on the binary star data, convinced that planets must exist in such systems. The first hints emerged in late 2010, when analysts studying the eclipsing binary system, designated Kepler-16, noticed additional small dips in brightness that could not be explained by the binary eclipses alone. The pattern showed transits occurring with a period of about 229 days, much longer than the 41-day binary orbital period, suggesting a planet orbiting both stars at a distance that made sense according to the theoretical stability predictions. The team spent months confirming the detection, ruling out instrumental artifacts, false positives from background stars, and every other possible explanation before concluding that they had found the first circumbinary planet. The announcement came on September 15, 2011, at a NASA press conference that revealed Kepler-16b to the world, describing it as a Saturn-sized gas giant, orbiting two stars in a configuration that immediately drew comparisons to Tatooine from Star Wars. The media coverage focused heavily on the science fiction connection, with headlines proclaiming the discovery of a real Tatooine planet. Though the scientists emphasized that Kepler-16b itself was far too cold to be habitable, and that any hypothetical moons would face similarly frigid conditions. The discovery proved that circumbinary planets existed in reality, that planet formation could occur in binary star systems, and that such planets could maintain stable orbits over the billions of years required for the system to exist. The success with Kepler-16b established the analysis methods and gave the team confidence to search the Kepler data for additional circumbinary planets, leading to a cascade of discoveries over the following years. Kepler-34b, announced in January 2012, showed a similar configuration with a gas giant orbiting two Sun-like stars, confirming that the first detection was not a unique fluke, but represented a genuine population of planets. Kepler-35b followed shortly after, and then Kepler-38b, each detection refining the techniques and building statistical understanding of how common circumbinary planets might be. The Kepler-47 system, announced in August 2012, represented a major milestone as the first binary system found to host multiple planets, with Kepler-47b and Kepler-47c both orbiting the same binary pair at different distances. The discovery demonstrated that circumbinary systems could host entire planetary systems rather than just isolated single planets, suggesting that planet formation in binary environments could produce outcomes similar to single-star systems, despite the gravitational complexity. A third planet, Kepler-47d, was discovered in the same system in 2013, making it the first confirmed three-planet circumbinary system. The total number of confirmed circumbinary planets remained relatively small compared to the thousands of planets found around single stars, partly because binary systems make up a smaller fraction of Kepler's targets, and partly because the detection process is more challenging. As of recent counts, fewer than 20 confirmed circumbinary planets exist in the catalogue, though the number continues to grow as analysis techniques improve and as new missions like TESS contribute additional detections. The small sample size means that statistical estimates of how common such planets are remain uncertain, with current data suggesting that perhaps a few percent to perhaps 10 or 20% of close binary systems might host planets, though the true fraction could be higher if many planets orbit at distances or inclinations that prevent us from detecting their transits. The detection methods extend beyond the transit technique, though transits remain the most productive approach for finding circumbinary planets given their geometric advantages. Radial velocity measurements, which detect the gravitational wobble that planets induce in their stars, become extremely complicated for binary systems where both stars already orbit each other and create their own radial velocity signals. Separating a planet's influence from the binary motion requires exceptionally precise measurements over long time periods. Though a few circumbinary candidates have been proposed based on radial velocity data that remains to be confirmed. Direct imaging, where telescopes actually photograph planets as distinct points of light separated from their stars, faces similar challenges because the close separation of binary stars makes it difficult to distinguish a faint planet from the glare of two bright stars. Future extremely large telescopes with advanced adaptive optics and coronagraphs may eventually directly image circumbinary planets, particularly large young planets that still glow with heat from their formation. But current imaging technology generally cannot resolve such systems well enough to confirm planet detections. The discoveries, therefore, rely primarily on the indirect method of transits. Reading the story of these distant worlds in the patterns of dimming starlight that reaches Earth after traveling hundreds or thousands of light years through space, the human element behind the discoveries deserves recognition, as the confirmation of each planet represents years of work by teams of astronomers, data analysts, and theorists who collaborate to ensure that detections are genuine before announcing them to the world. The process begins with automated computer searches flagging potential planet signals in the data streams from telescopes, creating lists of candidates that require follow-up investigation. Researchers then manually examine each candidate, looking at the light curves, checking for consistency, modeling the system to determine what configurations could produce the observed signal, and systematically ruling out false positives. The verification process often requires observations from multiple telescopes to confirm that the dimming occurs simultaneously in different wavelengths and from different observing locations, ruling out instrumental artifacts or background stars that might mimic planet signals. For binary systems, the modeling becomes particularly complex, requiring detailed understanding of both stars' properties, their orbital parameters, and how their combined light varies throughout their orbit. The final confirmation often comes only after months or years of analysis, with published papers documenting the detection typically running to dozens of pages, filled with data, models, and careful argumentation, demonstrating that a planet represents the only plausible explanation for the observations. The emotional experience of discovery, while not often discussed in scientific papers, drives the persistence required to find these worlds. Researchers describe the excitement of seeing a potential planet signal emerge from data, the frustration of ambiguous results that could mean either a planet or a false positive, the satisfaction of watching a detection strengthen as additional observations accumulate, and the joy of finally confirming that a new world exists. The Kepler 16b team recalled their growing confidence as the data accumulated, the nervous anticipation before announcing the discovery, and the thrill of seeing the press conference generate worldwide interest in what they had found. Each subsequent discovery brought similar feelings. The never-ending wonder at detecting worlds so distant that light takes hundreds of years to travel from there to here. The technological requirements for these discoveries remain impressive, with the Kepler telescope achieving photometric precision of about 20 parts per million, meaning it could detect brightness changes of 0.002%, sensitive enough to see the dimming caused by an Earth-sized planet passing in front of a sun-like star. For binary systems, the precision requirements become even more demanding because the planet's signal must be extracted from the much larger brightness variations that the binary eclipses create, requiring careful calibration and long-term stability of the instrument. The success of Kepler in finding circumbinary planets demonstrated that space-based telescopes with exquisite precision and continuous monitoring could reveal planetary systems too subtle for ground-based telescopes to detect reliably. The ongoing nature of the discovery process means that more circumbinary planets await detection in existing data and in new observations from current and future missions. The TESS mission, launched in 2018, surveys the entire sky looking for transiting planets around the brightest nearby stars, including binary systems, with several circumbinary candidates already emerging from TESS data that await confirmation. Future missions will push toward finding smaller planets, moving from the gas giants that dominated early detections toward Neptune-sized and eventually Earth-sized circumbinary worlds. The James Webb Space Telescope's ability to characterize planetary atmospheres will eventually extend to circumbinary planets, revealing what gases exist in their atmospheres and whether any show signs of interesting chemistry. The statistical picture emerging from the discoveries suggests that circumbinary planets represent a significant population of worlds in the galaxy, with thousands or millions of such planets likely existing, even if only a small fraction of binary systems host them. Extrapolating from the confirmed detections and accounting for the geometric probability that planets must transit from our viewing angle to be detected, astronomers estimate that perhaps 5 to 10% of close binary systems might host giant planets in the configurations where Kepler could detect them. The true abundance of circumbinary planets at all sizes and orbital distances remains unknown and will require future surveys with different techniques to determine completely. The legacy of these discoveries extends beyond the specific planets, found to the transformation of our understanding of planetary system formation and evolution. The confirmation that planets form in binary star systems demonstrated that planet formation is a robust process that operates even in gravitationally complex environments. That nature finds ways to create worlds in nearly every stellar configuration that physics allows. The discovery validated decades of theoretical work predicting circumbinary stability zones and showed that the universe implements the possibilities that our mathematics describe. And the discovery provided humanity with the knowledge that Tatooine-style worlds actually exist, that somewhere in the galaxy planets orbit beneath skies illuminated by two suns, and that the universe's creativity in forming planetary systems exceeds even the imaginative visions of science fiction. The journey from theoretical prediction through patient observation to confirmed detection illustrates how science progresses through the interplay of theory and observation, with each informing and refining the other. The circumbinary planets discovered so far represent the beginning of understanding these systems, rather than complete knowledge, with each new detection adding details and sometimes surprises that challenge existing models. The process continues, with researchers analyzing data, modeling systems, proposing new observations, and gradually building the comprehensive picture of how multi-star planetary systems work and how common they are throughout the galaxy. And each detection adds another world to the catalogue of places that exist, places with sunrises and sunsets, and orbital rhythms different from Earth, places we have never visited, but whose existence we can confirm through the patient reading of starlight that reaches us across the vast darkness between the stars. Among all the questions raised by the discovery of planets orbiting binary and multiple star systems, perhaps the most profound asks whether any of these worlds could support life, whether organisms could evolve and thrive under the light of 2 or 3 suns, and whether the universe might harbor ecosystems fundamentally different from Earth's, yet operating on the same basic principles of chemistry and biology. The search for habitable worlds beyond our solar system focuses primarily on finding planets where liquid water can exist on the surface, as water provides the solvent in which Earth's biochemistry operates, and likely represents a requirement for any life chemistry similar to ours, though the possibility of exotic biochemistries using other solvents cannot be ruled out entirely. The concept of the habitable zone, sometimes called the Goldilocks zone, defines the range of distances from a star where a planet's surface temperature could allow liquid water to exist, neither so close that water boils away, nor so far that it freezes permanently. For a single star like our Sun, the habitable zone forms a ring-shaped region extending from about 0.9 astronomical units to about 1.5 astronomical units, depending on the exact assumptions about planetary atmosphere and greenhouse effects, with Earth sitting comfortably within this zone at 1 astronomical unit. The boundaries shift inward for cooler, dimmer stars and outward for hotter, brighter stars, but the concept remains the same: a zone where conditions permit liquid water. For binary star systems, calculating the habitable zone becomes more complex because the stellar radiation comes from 2 sources that move relative to each other and relative to any orbiting planet. For planets in circumbinary orbits, orbiting both stars together, the habitable zone lies farther from the stars than it would for either star individually, because the planet receives radiation from both stellar surfaces, effectively doubling the available energy compared to a single star. The combined luminosity of the 2 stars determines where the habitable zone sits, with the zone beginning at a distance where the doubled radiation input creates Earth-like temperatures rather than scorching heat. The circumbinary habitable zone typically begins at distances greater than the binary separation itself, ensuring that the planet orbits far enough out that the 2 stars appear relatively close together in the sky, and that the planet's orbit remains stable over billions of years. For the Kepler-4/7 system, with 2 stars somewhat dimmer than our Sun, the habitable zone sits at roughly the distance where Kepler-4/7c orbits, making that planet the first circumbinary world discovered in a potentially habitable location. The planet itself appears to be a gas giant, roughly the size of Neptune, too large and lacking a solid surface to be habitable itself, but large enough that it could host moons, and any sufficiently large moon orbiting Kepler 47c might offer a habitable surface beneath the twin suns. For planets orbiting just one star of a binary pair, the S-type configuration we explored with Alpha Centauri, the habitable zone calculation resembles that for single stars, with an important addition. The second star provides supplemental illumination that varies with the binary orbital phase. When the planet orbits the smaller, dimmer star of the pair, the habitable zone lies closer to that star than it would to a sun-like star. But the companion star adds brightness that could shift the effective habitable zone inward, or create a more forgiving range of distances where liquid water could exist. The calculations become complex because the companion's contribution varies from maximum when the two stars align on the same side of the planet to minimum when they sit on opposite sides, creating seasonal variations in total radiation that overlay the planet's own seasonal cycles from axial tilt. The stability of the habitable zone over billions of years matters enormously for life's prospects, as complex life requires long timescales to evolve from simple chemistry to organisms and ecosystems. A planet that spends part of its orbital path in the habitable zone and part outside that zone might experience cycles of freezing and thawing, or boiling and cooling that prevent life from gaining a foothold, or that repeatedly sterilize the surface. The habitable zones around binary stars need to be permanently habitable, maintaining liquid water conditions throughout the full range of orbital and binary phase variations that the planet experiences. For close binary systems where the stars orbit each other quickly, the variations in illumination average out over short timescales, creating relatively stable conditions, while for wide binaries, the variations occur over years or decades, creating more pronounced seasonal effects. The stellar evolution complicates long-term habitability because stars change their brightness over billions of years as they age and exhaust their nuclear fuel. Our sun has increased in brightness by about 30% since it formed 4.6 billion years ago, shifting the habitable zone outward over time, with Earth remaining habitable partly through atmospheric feedbacks that helped regulate temperature. For binary systems, both stars evolve, though at different rates if they have different masses, creating complex changes in the total luminosity and in the habitable zone position. Planets in the habitable zone, when the stars are young, might become too hot as the stars brighten, while planets initially too cold might warm into habitability over time. Red dwarf binary systems offer particularly interesting habitable zone characteristics because red dwarfs burn their hydrogen fuel so slowly that they remain stable for hundreds of billions or even trillions of years, far longer than the current age of the universe. A planet orbiting in the habitable zone of a red dwarf binary could maintain habitable conditions for timeframes that dwarf the age of life on Earth, potentially allowing evolution to explore biological possibilities impossible in the shorter timescales available around sun-like stars. The trade-off comes in the close orbital distances required for habitable temperatures around such cool stars, placing planets well within the tidal influence of their stars and potentially leading to tidal locking, where the planet always shows the same face to its star or stars. Tidal locking, where a planet's rotation period matches its orbital period, creates day sides in permanent sunlight and night sides in permanent darkness, potentially concentrating ice on the dark side and creating extreme temperature differences between hemispheres. For single stars, tidal locking creates challenges for habitability, though thick atmospheres might redistribute heat well enough to prevent complete freezing of the night side. For binary systems, the dynamics become more interesting because tidal locking to a binary pair might stabilize the planet in a configuration where it rotates at a rate that keeps the binary stars moving across the sky rather than remaining fixed, creating more complex illumination patterns that could help distribute heat more evenly. The question of photosynthesis in multi-star environments adds another layer to habitability considerations. As Earth's plants evolved to capture energy from our sun's yellow-white light, with peak efficiency in the red and blue portions of the spectrum, plants on a planet orbiting two stars with different colors might evolve to capture energy from both spectral distributions, using pigments that absorb light across a broader range of wavelengths, or developing separate photosynthetic systems optimized for each star. A world orbiting a yellow star and a red dwarf might host plants that appear black to our eyes because they absorb both yellow and red light, or plants that shift their active photosynthetic system depending on which star illuminates them, changing color or behavior as different stars rise and set. The circadian rhythms that govern daily biological cycles on Earth, from sleep-wake patterns in animals to the opening and closing of flowers, evolved in response to the 24-hour day-night cycle created by Earth's rotation. On planets in multi-star systems, particularly those experiencing multiple sunrises and sunsets, or perpetual twilight, when at least one star remains above the horizon at all times, organisms would need to evolve different biological clocks. Life might synchronize to the longest cycle, treating the period when all stars are up as day and the period when all are down as night. Or might develop multiple overlapping rhythms responding to each star independently. Or might abandon strict circadian patterns entirely in favor of more flexible behavioral responses to current light conditions. The atmospheric retention becomes critical for habitability because planets orbiting close to red dwarf stars face intense stellar activity, including flares and coronal mass ejections that could strip atmospheric gases over time unless the planet possesses a strong magnetic field to deflect the charged particles. Binary systems with red dwarf components might subject planets to doubled stellar activity, though the orbital configurations that place planets in habitable zones often keep them far enough from the stars that stellar wind effects remain manageable. The presence of a companion star might actually enhance magnetic field generation through tidal interactions, helping protect planetary atmospheres through the same tidal forces that create locking. The possibility of habitable circumbinary planets captures the imagination because it suggests worlds fundamentally different from Earth, yet potentially life-bearing, places where evolution proceeded under twin suns and created ecosystems we cannot fully anticipate. The organisms on such worlds might take forms convergent with Earth life if the physical and chemical constraints lead to similar solutions, with fish-like swimmers in oceans and bird-like flyers in atmospheres, or might explore entirely different body plans and strategies adapted to the unique conditions of binary illumination. The intelligent life that might evolve on habitable circumbinary worlds would grow up seeing two suns in their sky, developing mythologies and cultures shaped by the binary nature of their stellar environment. Perhaps viewing the duality of their stars as fundamental to existence in ways single-star civilizations like ours do not. The statistical likelihood of habitable circumbinary planets existing somewhere in the galaxy appears favorable when considering that roughly half of all stars exist in binary or multiple systems, and that the discovery of circumbinary planets demonstrates that such systems routinely form planets. If even a small fraction of binary systems host planets in their habitable zones, and if a fraction of those planets develop the right size, atmosphere, and other conditions for surface liquid water, the total number of potentially habitable circumbinary worlds in our galaxy could number in the millions. The Kepler-4-7 system already shows that habitable zone circumbinary planets exist, and future surveys will reveal whether rocky Earth-sized worlds orbit in such zones, or whether gas giants hosting large moons represent the primary habitable configuration. The James Webb Space Telescope and future observatories will eventually characterize the atmospheres of circumbinary planets through transit spectroscopy, measuring which wavelengths of starlight the planet's atmosphere absorbs as the planet passes in front of its stars. The presence of water vapor, oxygen, methane, and other gases can be detected through these spectral signatures, revealing atmospheric composition and potentially detecting biosignature gases that might indicate biological activity. For circumbinary planets, the analysis becomes complicated by needing to separate the planet's atmospheric signal from the light of two stars with different spectra. But the same techniques that enabled detecting these planets in the first place will allow characterizing their atmospheres. The search for habitable circumbinary worlds represents part of the broader search for life beyond Earth, an effort that encompasses planets around single stars, moons in our own solar system, and anywhere else that liquid water and chemical energy might coincide. The advantage of including multi-star systems in this search is that it dramatically expands the potential habitable real estate in the galaxy, adding millions or billions of additional worlds to the inventory of places where life might exist. The discovery that planets form around binary stars and that some of those planets orbit in habitable zones demonstrates that nature exploits every opportunity to create potentially life-bearing environments. And it suggests that life, if it arises readily from chemistry when conditions permit, might be far more common than we would calculate if we considered only single star systems like our own. The philosophical implications ripple outward from the science, as the possibility of life under multiple suns challenges our unconscious assumption that Earth-like conditions, including a single sun, represent requirements for life, rather than just the conditions under which Earth's life happened to evolve. The universe might routinely create habitable worlds in configurations we initially thought too complex or unstable, and life might adapt to those configurations as readily as Earth life adapted to our single-star environment. The galaxy might be populated with civilizations that grew up under binary skies, for whom the concept of a single sun seems as exotic as binary suns seem to us, and whose art and literature and science developed from a fundamentally different experience of the cosmos. The quiet wonder of knowing that habitable worlds might orbit beneath multiple suns, that somewhere in the galaxy, life might have evolved in the light of binary or trinary stars, adds depth to our understanding of life's possibilities and our place in the universe. The circumbinary planets discovered so far show only that such worlds exist and that they orbit in various configurations, including some within habitable zones. Whether any actually harbor life remains unknown and might remain unknown until we develop the technology to study their atmospheres in detail, or until, in some distant future, we travel there to explore them directly. But the possibility exists, grounded now in actual detections, rather than mere speculation. And the ongoing search continues to reveal more examples and to bring us closer to answering whether life under multiple suns exists anywhere in this vast galaxy. The circumbinary and S-type planets discovered so far display a remarkable diversity of characteristics, from scorching hot worlds orbiting close to their binary stars to frozen giants in wide orbits, from massive Jupiter-sized planets to smaller Neptune-sized worlds, each one adding unique details to our understanding of how planetary systems form and evolve in multi-star environments. Taking a tour through several of these worlds, briefly visiting each to observe its particular character and conditions, reveals the range of possibilities that exist and the creativity with which nature assembles planetary systems in every configuration that physics permits. The journey begins with a visit to one of the hottest known circumbinary planets, a world that orbits two stars so closely that its surface temperature soars above 2,000 degrees Fahrenheit, hot enough to melt rock and vaporize metals. This scorching gas giant, similar in size to Jupiter or Saturn, completes its orbit in only a few days, racing around both stars at a distance that would place it well inside Mercury's orbit if it circled our Sun. The proximity to the binary pair means both stars appear enormous in the sky together, covering perhaps 30 or 40 degrees of arc, their combined light so intense that the planet's day side glows almost as brightly as the stars themselves from reflected radiation. The view from this hot world shows the two stars moving across the sky in lockstep, separated by only a small angle because the planet orbits so much farther from the binary pair than the stars orbit each other. The planet is almost certainly tidally locked, keeping one hemisphere permanently facing the stars and the other hemisphere facing away into eternal night, creating extreme temperature differences between dayside and nightside that drive powerful atmospheric winds rushing from the heated hemisphere to the cooler one. The sunset on such a world, if one could observe from the terminator region between day and night, would show both stars setting simultaneously, the brilliant binary pair sinking together below the horizon, while the atmosphere churns with winds reaching thousands of miles per hour. Moving outward to more moderate distances, the next stop visits a frozen world orbiting a pair of red dwarf stars. Two cool, dim M-type stars that together produce only a fraction of our Sun's energy. This planet, larger than Earth but smaller than Neptune, orbits at a distance that would be comfortably habitable around a Sun-like star, but receives so little energy from its two red dwarfs that its surface temperature never rises above -300 degrees Fahrenheit. The landscape consists of frozen nitrogen and methane ice, tinted pink and red under the illumination of the twin red suns, creating an alien Arctic scene of icy plains and frozen mountains beneath a deep red sky. The two red stars hang in the sky as small disks, perhaps appearing similar in size to how the Sun appears from Jupiter. Each one glowing deep red-orange together, providing about as much light as a very overcast day on Earth, but shifted entirely into the red end of the spectrum. The shadows cast by objects on the surface appear doubled, as we have seen before, though the faint illumination makes the shadows subtle and difficult to distinguish, except when both stars sit at low angles and cast long shadows across the ice. Night on this world, when both stars set, brings true darkness, with the surface temperature dropping even lower than the already frigid daytime temperatures, and the stars, scattered across the black sky, showing unfamiliar patterns from this distant corner of the galaxy. The tour continues to a mini Neptune orbiting a binary pair consisting of one sun-like yellow star and one orange K-dwarf star, with the planet orbiting both at a moderate distance that creates temperate conditions. This world, about 3 times Earth's diameter, likely possesses a thick hydrogen-helium atmosphere surrounding a core of rock and ice, with no solid surface, but perhaps a deep liquid water layer beneath the gaseous envelope, where pressure and temperature create conditions unlike anywhere in our solar system. The temperature, at the level where atmospheric pressure equals Earth's surface pressure, might reach room temperature, creating a layer of warm clouds floating in an endless sky, with no ground below and endless atmosphere above. The 2 suns, one yellow and one orange, move across this world's sky, separated by several degrees, with the yellow star appearing slightly larger and brighter than the orange companion. The combined illumination creates a white or very slightly warm-tinted light, the yellow and orange mixing to approximate daylight on Earth, though coming from 2 distinct sources. The clouds at various atmospheric levels might display different colors depending on their composition, with white ammonia ice clouds at high altitudes, brown or tan ammonium hydrosulfide clouds at intermediate levels, and blue or grey water clouds deeper still, creating layered structures of color that shift and flow with the powerful winds that circulate around the planet. Descending to visit a potentially rocky planet, our tour arrives at a world perhaps 40% larger than Earth, orbiting in the habitable zone of a close binary pair, receiving just enough combined energy from both stars to maintain surface temperatures, where liquid water could exist if the planet possesses the right atmospheric composition and pressure. The planet's size suggests it might be a super-Earth, rocky like our homeworld, but with higher surface gravity, possibly with a thicker atmosphere and deeper oceans if water exists there. The surface might show continents and seas, though any life or geological activity remains pure speculation, without detailed observations we do not yet possess. Standing on a solid surface on this world, if it exists, and if the planet indeed has continents, the landscape might feel almost familiar with rocky ground and perhaps liquid water in low areas, but the sky reveals the alien nature of the environment. 2 suns hang at different positions, one brighter than the other, both small enough to appear as disks, but clearly separate points of light, casting distinct shadows. The atmosphere scatters their combined light to create a sky color depending on the atmospheric composition. Perhaps blue if nitrogen and oxygen dominate, like Earth. Perhaps orange or pink if the atmosphere differs in makeup or density. Weather systems would circulate under the influence of both stars' heating, creating complex patterns that might include some features familiar from Earth and some entirely novel. The tour shifts to a moon rather than a planet, visiting a large satellite orbiting a gas giant that itself orbits a circumbinary system. This moon, perhaps the size of Mars or Earth, experiences multiple cycles of illumination from the two distant stars, from the gas giant it orbits, and from its own rotation. The view from the moon's surface shows the gas giant dominating much of the sky, with the giant planet displaying phases like our moon shows when seen from Earth, as the sunlit portion changes with the moon's orbital position. The two distant stars appear small but bright, their combined light providing moderate illumination when the moon faces them, while the gas giant provides reflected sunlight, creating a complex pattern of brightness that varies throughout the moon's orbital period. The tidal forces from orbiting so close to a massive gas giant likely keep the moon's interior warm through tidal flexing, possibly maintaining geological activity and even a subsurface ocean beneath an icy crust. If conditions align correctly, the moon experiences multiple sunrises and sunsets each orbital period as it rotates. And if it is tidally locked to the gas giant, one hemisphere always sees the giant overhead, while the other hemisphere never sees it at all, creating regions with permanently different sky views and different patterns of illumination from the combination of stellar and planetary light. Life on such a moon would need to adapt to complexity Earth organisms never face, with multiple cycles of light and dark operating simultaneously. Returning to gas giants, the next world visited shows a planet similar to Saturn, complete with a ring system that circles its equator, orbiting a binary star system where both stars are slightly smaller and cooler than our Sun. The rings, made of countless ice and rock particles, catch light from both suns, creating brilliant displays where the rings appear illuminated from two angles simultaneously. From the planet's cloud tops, the rings arc across the sky, and the shadows they cast onto the planet's upper atmosphere show complex patterns where double illumination from the binary stars creates overlapping shadow bands. The planet's many moons, perhaps dozens of satellites, ranging from small captured asteroids to large regular moons that formed with the planet, each experience slightly different illumination, depending on their orbital positions and distances. The innermost moons orbit inside the ring plane and experience eclipses each orbit as they pass through the planet's shadow, while the outermost moons orbit far enough out that they receive nearly constant illumination from one star or the other throughout their orbital periods. The system becomes a miniature planetary system itself, with the central gas giant, its rings, its moons, and the two distant suns creating a complex gravitational and illumination environment. The Diversity Tour concludes with a visit to one of the smallest confirmed circumbinary planets, a world only about twice Earth's diameter, orbiting close to a pair of red dwarfs, representing a transition between the large gas giants that dominate circumbinary detections and the smaller rocky worlds that future surveys will hopefully find. This planet's composition remains uncertain. It might be a small gas planet like Neptune or a large rocky planet with a thick atmosphere, but its moderate size suggests possibilities that the massive gas giants cannot offer. If rocky, it might have a solid surface, though the close orbit keeps temperatures too high for habitability, possibly creating a world like Venus with a thick carbon dioxide atmosphere and scorching heat. Each world visited during this tour exists somewhere in the galaxy, orbiting beneath the light of multiple suns, proceeding through its days and nights according to orbital mechanics and stellar positions that create patterns unique to multi-star systems. The hot Jupiter-sized planet races around its close binary. The frozen world circles distant red dwarfs. The mini Neptune floats in its temperate orbit. The potentially rocky super-Earth sits in the habitable zone. The Moon orbits its gas giant while receiving light from distant stars. The ringed planet displays its ice particles to two suns. And the smaller transitional world represents the bridge toward Earth-sized circumbinary planets. Together, they demonstrate that planetary systems form around binary stars in all the same size ranges and orbital configurations that single-star systems display, with the added complexity of multiple stellar components creating variations in illumination and gravitational environments. The ongoing discoveries continue to add worlds to this catalogue, with each new circumbinary detection revealing whether it fits existing patterns or presents novel characteristics that expand our understanding. Future missions with greater sensitivity will push toward finding smaller planets, hopefully reaching the regime of Earth-sized rocky worlds that represent the most interesting targets for habitability studies. The diversity already found, despite the small sample size of confirmed detections, suggests that the full diversity of circumbinary planets will prove as rich and varied as the thousands of planets found around single stars, with every possible combination of size, temperature, composition, and orbital configuration eventually represented in the catalogue. The tour through these diverse worlds provides perspective on the range of planetary environments that exist under multiple suns, from extremes of heat and cold to moderate temperate conditions, from gas giants to possible rocky worlds, from isolated planets to complex systems with multiple planets and moons. Each world operates according to the same physical laws that govern our solar system, yet the presence of multiple stars creates outcomes and experiences utterly unlike anything Earth demonstrates. The quiet beauty of this diversity, the knowledge that nature creates worlds in every configuration that physics allows, adds depth to our understanding of planetary systems and hints at the vast variety of environments that exist throughout the galaxy, waiting for discovery and eventual exploration. The future of multi-star planetary science extends from current observations through increasingly sophisticated detection methods toward eventual detailed characterization, and possibly, in the distant future, direct exploration of these alien worlds where multiple suns illuminate skies we can currently only imagine. The technological capabilities available today already allow detecting circumbinary planets and measuring their basic properties, including orbital periods, sizes, and approximate temperatures. But the next generations of telescopes and missions will reveal atmospheric compositions, weather patterns, and potentially even surface features if rocky planets can be found and studied in sufficient detail. The James Webb Space Telescope, launched in December 2021 and beginning science operations in mid-2022, brings unprecedented capabilities for studying exoplanet atmospheres through transit spectroscopy. Though its initial targets focus primarily on planets around single stars, where the analysis remains more straightforward. As techniques mature, and as researchers develop methods for handling the complexity of binary stellar spectra, JWST will eventually turn its attention to circumbinary planets, measuring which wavelengths of light the planet's atmospheres absorb when they transit across their stars. The absorption features reveal the presence of specific molecules, including water vapor, methane, carbon dioxide, and potentially biosignature gases like oxygen or phosphine that might indicate biological processes. The challenge for circumbinary spectroscopy lies in separating the planet's atmospheric signal from the combined spectrum of two stars with different temperatures and compositions. A mathematical and observational problem that requires precise understanding of both stellar spectra to isolate the tiny additional absorption caused by the planet's thin atmosphere. The rewards justify the difficulty, as confirming the atmospheric composition of circumbinary planets would reveal whether such worlds possess the same types of atmospheres as planets around single stars, or whether the dual stellar environment creates novel atmospheric chemistries. The detection of water vapor in a circumbinary planet's atmosphere would confirm the presence of a key ingredient for life, while oxygen detection would raise profound questions about biological processes occurring under twin suns. Future dedicated exoplanet missions, including proposed observatories like the Habitable Worlds Observatory or the Large UV Optical Infrared Surveyor, would bring capabilities specifically designed for characterizing Earth-like planets, including those in multi-star systems. These missions would combine large apertures to collect more light, advanced coronagraphs to block starlight while allowing planetary light through, and spectroscopic instruments optimized for detecting biosignatures. A rocky planet in the habitable zone of a binary system, if found and studied with such instruments, could reveal whether continents and oceans exist, whether clouds circulate through the atmosphere, and whether the chemical signatures of life manifest in atmospheric composition. Direct imaging of circumbinary planets represents one of the greatest technical challenges in astronomy, because the planets orbit far enough from their stars to avoid instability, but still remain lost in the stellar glare from our distant vantage point. The angular separation between a circumbinary planet and its binary stars, as seen from Earth hundreds or thousands of light years away, measures only milliarcseconds, far smaller than current telescopes can resolve, except in the most favorable cases. Future extremely large telescopes with apertures of 30 or 40 meters, equipped with adaptive optics systems that correct for atmospheric distortion, and coronagraphs that suppress starlight, may eventually photograph circumbinary planets directly, capturing actual images of worlds orbiting twin suns. The photographs, if achieved, would show the planet as a faint point of light near the brighter points of the two stars, with colors revealing something about atmospheric or surface composition, and with brightness variations over time, potentially indicating weather patterns, rotation, or even continents and oceans, creating brightness differences as the planet rotates. Multiple images, taken over months or years, would show the planet moving in its orbit, providing direct visual confirmation of the orbital mechanics we currently infer from transit timing and radial velocities. The psychological impact of actually seeing a photograph of a planet orbiting two stars, of viewing a real Tatooine world as an image rather than just data, would transform these worlds from abstractions into tangible places in the minds of scientists and public alike. The nearest multi-star system to Earth, Alpha Centauri, represents the most likely early target for detailed study, and possibly for interstellar probe missions, given its proximity at 4.37 light-years. The Breakthrough Starshot initiative proposes sending tiny, lightweight probes accelerated to 20% of light speed by powerful ground-based lasers, reaching Alpha Centauri in about 20 years flight time, plus 4.37 years for signals to return, making it possible to receive data from Alpha Centauri within a single human generation. If planets exist around Alpha Centauri A or B, or if Proxima Centauri's known planet Proxima b offers interesting characteristics, such probes could photograph them from close range, revealing details impossible to observe from Earth. The images from an Alpha Centauri probe would show what planets in a multi-star system actually look like from nearby, revealing surface features, cloud patterns, colors, and the appearance of the binary companion star as seen from the planet's vicinity. A flyby of a habitable zone planet around Alpha Centauri b would show Alpha Centauri A as an incredibly bright star in the sky, exactly as we explored in earlier parts, confirming through photography what we currently only imagine through calculation. The data returned would likely include spectra revealing atmospheric composition, surface temperature maps showing climate patterns, and images of any moons that might orbit the planets, transforming our understanding of the nearest multi-star system from astronomical measurements to detailed knowledge comparable to what we have about planets in our own solar system. The more distant future, beyond current technology, but within the realm of theoretical possibility, includes crewed missions to nearby stars, including multi-star systems if faster propulsion systems can be developed. Generation ships traveling for centuries, suspended animation enabling long journeys, or breakthrough propulsion technologies allowing travel at significant fractions of light speed would make actual human exploration of circumbinary planets possible, allowing people to stand on the surfaces we have discussed and watch with their own eyes as multiple suns set in sequence across alien skies. The timescales for such achievements remain uncertain, likely measured in centuries rather than decades. But the physical laws permit them even if the engineering challenges exceed current capabilities. The cultural impact of confirming that life exists on a planet orbiting multiple stars would rival the Copernican revolution in reshaping humanity's view of its place in the universe. The discovery of microbial life under binary suns would demonstrate that life arises wherever conditions permit, that the chemistry leading from simple molecules to self-replicating organisms operates on circumbinary worlds just as it apparently operated on Earth. The discovery of complex life, of multicellular organisms or ecosystems, would show that evolution explores complex forms under alien illumination patterns, just as it did on Earth. And the detection of intelligent life, civilizations that arose under twin or triple suns, would prove that consciousness and technology develop in multi-star environments, that the path from chemistry to intelligence does not require single-star conditions. The perspective shift from viewing our solar system as the template for planetary systems to understanding that we represent only one configuration among countless possibilities continues to deepen as more exoplanets are discovered and characterized. The single sun that illuminates Earth begins to appear as an unusual case, rather than the standard when we recognize that most stars exist in binary or multiple systems, and that planets form routinely in such systems. The children of future generations may grow up learning that most planets experience multiple sunrises and sunsets, that Earth's single sun represents the minority case, and that the diversity of planetary illumination patterns exceeds what any single world can demonstrate. The 4 sunsets that began our journey, the sequential setting of suns on a circumbinary world, now carry deeper meaning, enriched by understanding the orbital mechanics that create them, the real planets where they occur, the variety of multi-star configurations that exist, and the possibility that life might witness them on worlds we have detected but never visited. Those sunsets happen every rotation period on Kepler-16b and on every other circumbinary planet, with multiple stars visible from its surface. The pattern repeating billions of times over the lifetime of the systems, witnessed by no one but occurring nonetheless according to the predictable mathematics of gravity and motion. The beauty exists independent of observation. The dual shadows and changing light and sequential farewells to daylight, all proceeding whether anyone watches or not. The ongoing work of discovering, characterizing, and eventually studying these worlds in detail continues in observatories and universities and space agencies around the world, with researchers analyzing data from current missions, planning future observations, developing new technologies, and gradually assembling the comprehensive picture of how common multi-star planets are and what conditions they harbor. Each new detection adds a data point. Each characterized atmosphere reveals chemical details. Each theoretical model refined with new observations brings understanding closer to completeness. The process unfolds over decades and will continue over centuries as humanity's capability to study distant worlds improves and as our reach extends farther from our single-star home system. The wonder that draws astronomers to study these systems and that draws curious minds to learn about them stems from the same source that makes any exploration meaningful. The recognition that the universe creates outcomes we can imagine but have never experienced, that reality exceeds our daily experience in both scale and diversity, and that understanding these distant worlds enriches our comprehension of nature's possibilities. The planets orbiting multiple stars exist as real places with their own characteristics, their own daily and seasonal rhythms, their own geological or atmospheric processes, all proceeding in configurations that differ from our familiar single-star arrangement. Knowing they exist expands the realm of the real, transforms science fiction tropes into astronomical facts, and reminds us that the universe's creativity in assembling matter into complex systems exceeds even our imaginative capacities. Standing conceptually on any of the worlds we have visited, from Kepler-16b to Alpha Centauri's potential planets, to the hypothetical habitable worlds in distant circumbinary systems, looking up at the sky where multiple suns hang at different positions, watching as they move and set and rise according to orbital mechanics and rotation, creates a connection across the vast distances that separate us from those worlds. The light from those stars left their surfaces years or centuries or millennia ago and travels through the emptiness between stars to eventually reach Earth, where our telescopes capture it and our instruments analyze it and our minds interpret it to understand what exists at the source. The connection exists as a flow of photons carrying information across the galaxy, bridging the distances that currently prevent physical travel, but cannot prevent observation and understanding. The journey through multi-star planetary systems, from the immediate experience of watching sunsets through the mechanics of orbits, to the real detected planets, to questions of habitability and future exploration, reveals a corner of galactic diversity that astronomy has only recently confirmed to exist. The theoretical predictions that planets could orbit binary stars have given way to actual detections. The speculation about what such worlds might be like has been grounded in measurement and observation, and the universe has demonstrated once again that it implements the possibilities that physics allows. The multi-star planets exist. They orbit in stable configurations. Some sit in habitable zones, and the future will reveal more examples and greater detail, until these alien worlds become as familiar to our understanding as the planets of our own solar system have become through centuries. Observation. And so the 4 sunsets continue on Kepler 16b and on worlds not yet discovered, the suns setting in sequence as they have for millions or billions of years, the double shadows shortening and merging as each sun approaches the horizon, the light shifting from the combined illumination of both stars to the illumination of one alone. The second star following the first into darkness, and finally, true night arriving after the last sun has set. The pattern repeats with each rotation, reliable as orbital mechanics, beautiful in its complexity, and real in a way that transforms imagination into fact. The universe contains such worlds, places where sunset comes more than once each day, where shadows double and light blends from multiple sources, where the sky reveals stellar configurations that Earth never shows, and where the ancient dance of multiple stars creates daily rhythms unlike anything our single sun can produce. Beneath skies we are only beginning to comprehend, through the patient work of discovery that continues, revealing one planet at a time, the diversity of worlds that orbit among the stars.